what to build on, what makes them different. And so I think probably the first thing you've probably heard of is optimistic versus ZK rollups, right? So I think the thing to note specifically, again, we talk about data availability. When we post that data back to Ethereum, how do we prove it's true, right? So there are two approaches. Optimistic rollups came first. What they do is optimistically assume that data is valid. So they implement something called fraud proofs. What this means actually is when we do something called withdrawals, so withdrawals being bringing like ETH from the L2 back to the L1, they have to implement something called a challenge period. So a challenge period is 7 days, basically, where it's locked up and gives the community to opportunity to essentially dispute the transaction. And so what that looks like is it say, hey, I want to dispute that within the 7 days, and then we will submit a fraud proof, validate that fraud proof, and then if it's good, then we're good to go. For bad, then oh no, you know. The downsides of this, right, is a few things, right? It requires at least one honest node. So obviously there has to be a good person, I guess, going through and doing the fraud proofs. The other thing is this needs to post all the transaction data back to the L1, right? Because what it needs to do is like recreate the history of everything going on. So that is something I will touch upon when we talk about ZK rollups, right? So ZK rollups was kind of the next phase of rollup architecture. This is when we think about, okay, rather than optimistically assume, let's actually submit something called a validity proof upon submission of that data back to Ethereum. And so what this does is allows us to like create mathematical guarantees around validity, creating safer trust assumptions, security guarantees, as well as when I talked about finality before with the challenge period, you don't have to do that, right? You can submit it and then it's verified immediately. I think there are a few things I want to note here that I get a lot of misconceptions about. ZK, which we'll dive into a little bit later, right, is very popularly known as something we use in privacy. With regards to rollup specifically, depending on the ZK rollup, privacy is not necessarily guaranteed. So the use case of ZK proofs in this situation is posting that proof back to Ethereum is expensive, right? Every time we interact with Ethereum, that is expensive. So we want to bring the smallest type of proof back. And it just so happens because ZK proofs have the property of not having all of the information revealed as part of that, is kind of the most, smallest proof. That's not correct English grammar, but you get me, right? To be put back. So the last thing about that too, right, is like we only need to post like transition state data back to the L1 rather than everything as compared to optimistic rollups. So some examples you might know, I put up logos, Scroll, ZK Sync, you might know, what's it called, Linea, Polygon ZK EVM, lots of interesting players in the space. Let's go a step deeper. Okay, we've covered the optimistic rollups. We've covered the ZK rollups, but let's actually differentiate within the ZK rollup itself, right? How do we start thinking in that design space? So the first thing I need to talk about is the ZK EVM. So essentially what you can think of a ZK EVM as is like a magical computer that allows us to execute EVM code, so you can write Solidity smart contracts, but also allows us to kind of translate that into something that is provable, right? Because ZK proofs are math, and how do you turn code into math? I'm not entirely sure. Ask our researchers and engineers, but that's what a ZK EVM essentially allows you to do. This is incredibly difficult to do just based on how the EVM was built, which has given rise to 4 different types of ZK EVMs. So this is kind of where we start talking about, okay, how did the ZK rollups differentiate themselves from each other? So at a high level, type 4 is going to be something that we call high language level equivalent, but not bytecode equivalent. So an example would be like a SNARK or a ZK Sync. What this means for developers specifically is you can write in Solidity, but your tools will have to change to an extent, right? Because it's not to kind of understand the information. Type 3, I'm going to gloss over as sort of the transitionary period to type 2, which is kind of the next stage. I put a frog there because I like this one. But anyways, this is a high-level language equivalent, so the same thing. You can write in Solidity, you can write in Viper, etc. But it is a bug in Viper that caused a hack, right? And the problem was not in the Viper code itself, but actually in the compiler, right? So if you map that same paradigm to ZK EVMs, right, you can kind of audit all of the smart contract code, but there's a lot stronger, at least in my opinion, of a security guarantee when at the lower level, you don't have that overhead of thinking how it's different as well. So that's type 2. Type 1 is kind of fully Ethereum equivalent. So again, like I said, high-level language equivalent, Ethereum equivalent, meaning you can write in Solidity, tools don't change, and there's some little tweaks about like data and hashing that makes it the same. But anyways, the point of like also why you would choose different ZK EVMs is basically, like I said in the beginning, EVMs or ZK EVMs are really hard to build, right? So something like a StarkNet and ZK Sync took the stance of like, EVM's not perfect. Let's actually change it a little bit in order to get certain advantages, like maybe it's faster, maybe we have native account abstraction built in, versus maybe protocols more like Scroll or Linea, where we talk about, no, we want to maintain faithfulness to the EVM because that's where the community is. It just smooths the developer experience, things like that. Everyone's super cracked and super smart, so I'm not going to say one is better than the other, but I think something to think about as devs when you're comparing the landscape. Other things to think about, because we love numbers when we talk about rollups, is the different stages. So stages was something that was defined by L2Beat. If you guys aren't familiar, L2Beat is a really great resource to look up, like, I guess, rollup information that tells you about like different security guarantees, like their activity and stuff like that. They define 3 different stages of rollups. So again, when you're thinking about the layer 2 landscape, there's different I guess what we call training wheels that we have as the technology progresses over time, right? So stage 0 is where I would say most of the rollups operate right now. The most important thing to think about there is pretty much like the operators are centralized. So operators being like sequencers. You might hear that phrase a lot, centralized sequencer, right? The source code is available for you to reconstruct state. Stage 1 is kind of the next step, right? How do we let go of those training wheels a little bit more? So then that's when we bring in smart contract governance. This is when we introduce something called a security council, right? So security council is like a group of people who are going to basically arbitrate whether or not an upgrade might be made, things like that. There are specific requirements about like some of the security council people should be on the team itself and some should be external as well, right? And stage 2 is like, woohoo, no, we're completely training wheels off. It's fully managed by smart contracts. Proof system is permissionless. Security council is only there to basically handle like upgrades, or sorry, not upgrades, soundness errors. So if there's a bug, like creating an avenue to basically say, okay, are we going to upgrade this, making sure we have a good amount of time for users to exit if they don't want to be part of that upgrade. But also another kind of design space to think about when you're looking at the L2 landscape. And so to kind of summarize everything that we've talked about, there's a lot of trade-offs that fit everywhere here. At the highest level I wrote, by highest level I mean it's the first bullet point, finality is what I was talking about. So when you think about challenge periods in optimistic versus ZK rollups, that might be something you think about when it comes to liquidity fragmentation, stuff like that. I'm going to anticipate a question in case somebody might ask, like, oh, wait, when I withdraw from like an optimism to Ethereum, it feels instant. I don't understand. Where's that challenge period coming in? So just to address that point specifically, you might think about bridges, like third-party bridges, basically having separate liquidity pools to allow you to give that feeling. As we all know, bridges are the most like hacked space in the kind of ecosystem right now. But, I mean, there's a lot of strong guarantees that are happening that I'm not a bridge builder, so ask somebody else about it. But anyways, last piece, second piece, right? Like I said again, security guarantees and trust assumptions. So whether or not you're optimistically like waiting for a fraud proof versus saying I'm going to submit a proof on submission. Yeah, validity proofs. And to that extent, thinking about throughput, cost, again, there's a lot of different implementations that have trade-offs. Maybe if you're building a game, you might want something that is faster and cheaper with fewer security guarantees than a different type of app. Developer experience, so this is a trade-off when I was talking specifically about the different types of ZK EVMs and what you're willing to kind of, I guess, appetize. What you have appetite for. Decentralization, open source software, community. So this is kind of when you get into the ecosystem side of things. So how much do you care about those parameters? And like I said, again, network effects. So that not only affects like how connected are you to Ethereum, for example, but in your ecosystem itself, if you are a builder, what other builders can you interact with, like kind of additive things. So that is rollups at a very high level. I'm going to scare you guys a bit. Rollups are not the end game. They can still be very expensive. Why? So, like I said, oh, I heard some chuckles. Let's look at this again. But anyways, let's dive into maybe something that is a bit more of a current event, right? So like I said, when I talked about data availability, that's putting data back on Ethereum. But what do we remember about Ethereum? Every time you interact with it, it is very expensive. So how do we get around that, right? So this is something called EIP 4844, which was introduced, I think, sometime this year, which essentially created something called blobs, right? So blobs are a separate type of data structure than what was traditionally known as call data. So before, you would post information to something called call data, and call data is permanent and there forever, right? The thing about rollup data, right, is you're really only posting it there for like verification. So it doesn't need to be there forever, right? So blobs are actually an ephemeral type of data storage. It will like go away, I think, after 18 days. I'm not the most current on that exact number. But essentially what that does is allow us to use a different type of space. The other thing that is really cool about this as well is it is a separate fee market. So when it comes to competing for, like, I guess, data on Ethereum, blobs are a completely separate space. So what that looks like or means for rollups is you are not as exposed to the fluctuations in the market on Ethereum versus in call data versus blob space. So I guess the result is this is actually still not the most perfect solution. That's when you might start hearing things about like sharding, dank sharding, things in the future of the Ethereum protocol, but just think of this as, again, a high-level primer on what you can expect for the rest of Devcon. So other things that I just want to kind of say to put words in your head is there are, other scaling solutions that have kind of produced or been created. So you might hear something called a validium. So a validium is basically a chain that does like off-chain computation, proves via validity proofs, but they use off-chain DA. So another kind of buzzword to think about is now we're talking about data availability layers. I don't work for these companies, so I can't go too deep into them, but if you want to investigate EigenDA, Celestia, Avail are kind of the new design space you might think of there. And Optimium, I forgot an I, is basically optimistic rollup plus off-chain DA. And then the last one is going to be called a volition. So a volition is essentially the marriage of a validium and a ZK rollup, where you can kind of switch between whether or not you want to do on-chain DA versus off-chain. If you're looking for specific examples, again, head to l2beat.com. It'll actually list a bunch of different projects in the space and also what they are. Okay, cool. I don't know how much time I have left. I figured I would be talking for a long time. So, okay, my backpack is back there. I have swag for somebody who shouts out the answer here. Okay, which type of ZK EVM is bytecode compatible? ABCD. Okay, those are all numbers and not letters. I don't know. The answer is H. Everyone is right. Or not everyone is right, I guess. But, okay, this didn't work out as well as I thought. I did not think there would be this many people here. But thank you for participating. Okay, let's move on. Let's talk about zero knowledge. Okay, so this is some knowledge about zero knowledge. Basically, at a high level, right, zero knowledge proofs allow for a prover, so a person to prove to another person, the verifier, that they know something without revealing the information itself. Right? So what does that mean specifically? So when it comes to ZK proofs, there are three main properties. We think about completeness of the proof. So that means if the prover knows the information, they can convince the verifier with their proof. Soundness means if the prover doesn't know the information, they can't trick the verifier. And then zero knowledge is, like, I guess, pretty self-explanatory. The prover doesn't have to reveal any of the actual information itself. So there are two types of ZK proofs that we're going to get into, something called interactive proofs. So this is a type of proof that requires back and forth between the verifier. An example that is pretty common, you can just Google ELI5 interactive proofs, and this is a picture you get from Chainlink. Essentially what it is this example says, okay, I have Bob and Alice, and there is a magic door in a cave. And the magic door has a magic code that Alice knows, but Bob does not. So Alice wants to prove to Bob, hey, I know this code, but she doesn't want to tell him he knows this code, right? So the process basically looks like you have path A and path B into a magic door that Bob can't see. And so Alice will randomly choose a path, and then Bob will say, come back from path B, and then she'll come back from path B. And he's like, come back from path A, and she'll come back from path A. So what you can think of this as, if he asks her enough times and she can consistently come back in whatever direction that he wants her to come, that means she was able to cross that magic door, and therefore she also knows what the secret code is. So that's interactive proofs. When we talk about non-interactive proofs, that's basically saying the prover can say, hey, I'm going to give you one proof or like one piece of information, and the verifier says that's all I need to know. We don't need to interact past that, right? So the example here is about proving that I have completed a Sudoku puzzle. This is a little bit more complicated, so I'm going to dive into it deeper, but this is going to be what we think about when we talk about ZK rollup space, SNARKs, validity proofs, etc., right? So the way this works is actually something called hashing. So hashing is a one-way transformation of data. So that means like if I say, oh, I did 1, 2, 3, 4, 5, 6, 7, 8, 9, I can hash it and give you some like long string of letters, and you won't know the actual letter. But what you do is you basically hash each cell's number in the Sudoku puzzle. You combine all of those hashes in commitments for rows, columns, grids. I guess I'm just assuming everyone knows how Sudoku is played, but maybe you don't. So I'll step back again and also explain how Sudoku is played, in case you don't know, because we're all about starting from the top. Essentially, Sudoku is this grid, and what you need to do is be able to count 1 through 9 from the top to bottom, 1 through 9 across the rows, and 1 through 9 in each box, and there's no duplicates. Okay, cool. We all know what Sudoku is. If you take anything away from this talk, I hope you remember that specific piece. But essentially what you can do is create all these like commitments of the different forms of all the ways you created a Sudoku puzzle. And essentially the verifier is able to use cryptographic algorithms to understand, hey, yes, everything you sent me is, every row you sent me fulfills the requirement, every column you sent me fulfills the requirement, et cetera, but I don't actually know what the solution is, right? So that's how a non-interactive proof works. So now let's actually talk about SNARKs versus STARKs. So maybe this is also something you've kind of heard and been like, huh, what? Okay. So we'll dive into it, right? So SNARKs are succinct, non-interactive arguments of knowledge. So these are ZK proofs that are succinct, so they're small in size. They're non-interactive, so that means they don't interact with each other like the prover and verifier. These are very compact proofs that allow for fast verification. Thing to note is they do require a trusted setup. So a trusted setup is a pre-processing phase that allows basically creators to create a public and secret key for, like, I guess, the actual proving. The secret key needs to be thrown away, so this is kind of, I guess, a con of ZK SNARKs, which we can talk about a little bit later in the next slide. How do we solve for this? So again, another acronym that I heard, and I was like, what is this? And I'll just explain it very quickly. If you heard MPC, you might hear it later. This is called multi-party computation. This is allowing basically a more secure way of generating those keys, right? So rather than just like a single instance of like public key, private key, MPC essentially allows every participant to have a part of a private key and then work together without revealing their part of the private key to create the full one, right? So, I mean, there are trade-offs again, right? This doesn't scale really well when you have a lot of parties. It is vulnerable to collusion if like there's, I guess, non-good participants. But I'll give another example. So imagine all these frogs are pirates. And imagine all the pirates are looking for the secret treasure map. So they want to complete the treasure, but they don't want to show each other what piece of the map they have. So what they actually do is they divide each of their pieces into a bunch of smaller pieces and give everybody one part of their smaller piece. So no one knows your complete picture of what your piece is, but at the end of the day, everyone does have every piece necessary to create the full map. So that's NPC in a nutshell, with frogs and pirates. Okay, moving on. Let's forget everything. Actually, don't forget everything, but now we're going to talk about STARKs. So STARKs stand for Scalable Transparent Argument of Knowledge. So this is transparent because you don't require a trusted setup. It's also non-interactive. This is really good for handling very large, complex computations. However, the problem with them is they have larger proof sizes as compared to SNARKs. And so this is where we thread again through data availability, right? The size of that proof is very important for when we post it back to the L1, because if it's bigger, it's more expensive, right? So, I mean, again, these are different kind of ways that rollups have for move forward. So like a Starkware handles ZK Starks. However, not all is lost. Another interesting design space that I'm just telling you about that I learned, right, is I guess math is cool because you can put math on top of math. And so what that looks like in some solutions is you have a Stark, which is very good for computing large, complex computations. And then you wrap it, you prove that it was true in a SNARK, which is really good for making it smaller. So an interesting thing to think about. But anyways, at a glance, you can kind of see SNARKs have a trusted setups, Starks doesn't. I put this here. Post-quantum means quantum resistant. Basically, SNARKs right now, quantum computers aren't there yet, so please sleep soundly. But in the case that quantum computing gets there, SNARKs aren't necessarily quantum resistant. Starks will be. Like I said, when it comes to developer tooling, Starks are less, I guess, adopted, so there might be less information in the space. When we talk about, I guess, a ZK or a Starkware, for example, they'd use Starks, they have to use a different VM, they have to use different, I guess they write in Cairo, for example. So super smart team. It is a little bit different if you're like a Solidity dev moving in. And then I'm going to move forward. Hello. Yes. No. So post-quantum, I should have used like the layman's term. So post-quantum means possibly quantum resistant. So what that means is quantum computers are not at a stage that they can hack stuff yet, or hack SNARKs, right? But, you know, maybe we get into a world where that is. The way SNARKs are created is something called elliptic curve cryptography. I'm not going to explain it because I'm going to butcher it, but Starks use like random hashing, and basically hashing is going to be quantum resistant, but elliptic curve cryptography, whoa, that's a mouthful, is not. But we're not at the stage yet where we're thinking about it, but yeah, cool. Good to know. I will not write post-quantum anymore because it is confusing. Thank you for that. In the front. Okay, another quiz time. I put stretch sesh because I also expected people would stand up and be like, I'm tired, but I guess no one's tired. Oh, nice, thank you. Okay, what does SNARK stand for? Oh, perfect. Okay, I don't have enough swag for everyone who answered, but if you find me first, you will get a magnet. Okay, moving on. We have 30 minutes left, so hopefully we can get through everything. This is where we just get into current events, things I see on Twitter that people argue about that probably don't really matter in real life, but whatever, we're here talking about it. So let's talk about rollups, right? I went over optimistic rollups, I went over ZK rollups, but did you know people define more types of rollups? Let me list all of them for you that I saw on Twitter recently. Sovereign, enshrined, based, modular. Yes. Okay, cool. So let's actually just go through kind of, I have like a slide per each. We're going to define it, and then you can find people who work at those protocols to explain it to you further. But before we start off, we have to start from just kind of the base idea of modular blockchains, right? So modular versus monolithic. Monolithic blockchains do everything. They do consensus, they do settlement, they do DA, and they do execution, right? So something like a Solana would be a monolithic blockchain. Technically, Ethereum was a monolithic blockchain until the rollup architecture was introduced, right? So modular blockchains do a subset of that. So they might only do execution, they might only do data availability, they might do a subset and multiple. And so that's kind of when we get into all these new definitions of sovereign, based, enshrined. I said something else, I don't remember, but we'll get into it. Okay, cool. So now we start with the basics again, right? So what I talked about before, you know, rollups you might know today, Optimism, Scroll, Starknet ZK Sync, Linea, Polygon ZK EVM. I'm sorry if I didn't name you and you work on that protocol. I respect you. I just don't remember you right now. But essentially what those are going to be what we call now smart contract rollups, right? So those are controlled by smart contracts stored on the L1. What they do is, again, again, like I said before, store rollup state, track deposits withdrawals, handle verification. Key takeaway here is they mainly handle the execution part of it. The other key takeaway here is something we're going to get into when we talk about enshrined rollups. So enshrined rollups are different from smart contract rollups in the sense that they integrate with the L1 at the consensus level. So that means something has happened at Ethereum core that they are now interacting with. What that means specifically is when we talk about smart contract rollups, right, we have an external party determining what that smart contract looks like, right? We need security councils, multi-sigs. You need a bridge for L2 upgrades. So when we talk about enshrined rollups, you don't need all of that, right? Because it's enshrined within Ethereum itself. For a ZK EVM enshrined rollup, like validators don't have to re-execute everything because everything's enshrined in Ethereum. The cons here are going to be VM inflexibility, right? So in this case, you're married to whatever the L1 VM is. The cool thing that I will talk about at the end of this presentation is about all the new different types of VMs that are coming about that's helping with scaling, right? So you lose that. The other part is like it's slower to upgrade. You don't move as fast in terms of like development. It might be more complex. But there are pros and cons, like I said, and there is a space where actually both of them live together. So we're all a happy family. Cool, moving on. Oh, I put a logo here. This is Tezos. So Tezos is an L1 blockchain, if you don't know them. They are doing enshrined rollups in some capacity. I don't know how, but find a Tezos person and they will tell you. That's my tip for Devcon week. The other piece you might have heard of is based rollups. So based rollups is, I guess, not the traditional term of like you find in Urban Dictionary, but this is, I guess, the nerd sniping term for people who are interested in Tycho, right? So based rollups basically use the L1 for sequencing. So if you remember when I talked before about operators, right? Operators are a centralized sequencer that kind of take everything together. Base rollups basically use Ethereum for sequencing. So what this allows us to do is inherit the decentralization of Ethereum and inherits the liveness of the L1. So if Ethereum goes down, the sequencer goes down, like we were FUCKED anyway, versus like a centralized sequencer going down. That's a different case, right? And it is simpler when it comes to like decentralization of the sequencer. The con part of it, right, is if you want to get into it, we can talk about it after. I'm not going to go over it here. But there are different performance improvements that rollups do by like fixing the way they sequence stuff that you obviously won't get in this case. And the other part, maybe a good thing or a bad thing, depending on who you are. MEV that happens is going to be taken at the L1 level. You no longer get like the sequencer MEV from L2s, right? Because L1s are handling sequencing. The last piece we're going to talk about here is sovereign rollups. So sovereign rollups are kind of like I choose everything myself because I am sovereign. So what that means is I choose my own execution. I choose my own settlement layers. The pros here basically are, again, talking about like that forced upgrade from smart contract rollups, right? So smart contract rollup upgrades, if you want to participate in the L1, or if you don't want to participate in the L2, you just have to exit, right? Because the smart contract is upgraded. Sovereign rollups are actually like, hey, we're going to choose our own settlement. We're going to choose our own execution. We're going to do everything our same. It's what you can think of as the nodes control how they interact with each other. So what that looks like is in order to upgrade a sovereign rollup, you have to actually fork like a traditional L1. And so that allows us to basically kind of maintain whatever state we had before if you don't want to participate in the upgrade. The interesting thing here is, right, like this is a design space where we might be using Ethereum or Bitcoin as purely data availability and then not care about like consensus, settlement, et cetera, maybe with somebody else, right? I didn't put a logo here, but if you want to read more about it, Celestia is a project that is working a lot on sovereign rollups. But yeah, so section 4 is like other niche topics that aren't handled by rollups. I don't know how much time I left, but I think I have, yes. This is what I read online. So the answer is yes, as far as Google and an article that I read is correct. Cool. So let's dive into other hot topic. So something you might have heard of recently is trusted execution environments. So trusted execution environments is when we start talking about hardware with regards to privacy and scaling, right? So a TEE is essentially an area within a computer's processor where you can run code, but nobody else can access it. So like the OS actually can't even access that space, right? What this means, it is isolated. So it creates something called a secure enclave, is something you might have heard of, within the main processor. Only pre-authorized code can run here. It has something, not every TEE has this, but some of them do. They have attestations, right? So TEEs that you might use can produce an attestation to prove to others that the code is running is genuine and unmodified. Sorry, I just burped. And the last piece is confidentiality. Like I said, because this is a separate part of the, I guess, the hardware, you get to do stuff that's encrypted and inaccessible to the rest of the system. So something that's really important maybe for like privacy solutions in that new space, right? When we think about it further, actual TEE providers you might have heard of or now know, because I am saying it right now, Intel SGX is something. It's going to be a hardware provider. AWS Nitro is a TE provider, but they're more of a virtual machine. And like I said before, this supports use cases like privacy. It actually protects against MEV, which is a really interesting space. Flashbots is doing stuff in that direction. If you want to Google Flashbots, TEE, MEV, that would be a good place to start. There's a question. Sorry, what? Oh, yes, yes. There's ARM and Trusso, and I didn't list all of them. There's a few, but I only put 2. I should have put all of them. Thank you for that. But moving on, why we care about TEEs, right? It's a hardware secure environment. But to that point too, it is going to be vulnerable to whatever hardware specific attacks there are. You are putting trust in a different party, such as an Intel, such as an AWS, which comes with its own trade-offs. But these are very battle-tested, widely used projects. It allows for fast computation with hardware acceleration. I think the con side is when we talk about like participating in networks, if you require a TEE in order to run, i.e. specialized hardware, it might prevent certain people from participating in the network. And then integrity guarantees, they have attestations, but again, like I said, it does require trust in the hardware manufacturers. So whatever you have appetite for. But actually, this is something interesting I want to dive into when we talk about a particular use case of TEEs when it comes to rollups, so the L2 design space, right? And I mentioned before something called multi-provers. So this is a new buzzword that you should keep in your mind. So essentially, if we look at systems today, we have basically a single proof system. So if there's a bug in that proof system, that's a vulnerability, right? So now there's a new thing that Scroll has done. I believe Tycho has as well. If somebody else is doing, please let me know, called multi-provers. And what this essentially says is we want multiple proof implementations to basically reach a consensus of truth in order to like strengthen the security guarantee, right? There's different ways to do multiple proofs, right? We have fraud proofs, but that will introduce, I guess you could say, the challenge period. So you have the problem of finality running in again. Another way is just build a second ZK EVM because you're crazy. So do it if you want. I don't recommend it. Or maybe recommend it. I don't know. And the third piece that Scroll at least is moving forward with is doing a separate TEE, right? So we're doing the transaction in a TEE as well, generating proofs there. And the way we're actually doing it, again, when we think about having multiple implementations, we are doing via different types of hardware. So if you see Intel, SGX, AMD, AWS, things like that, I guess another cool thing to think about when you're considering the rollup space. What else do I have? Yes, okay, this is the last piece. And I have 50 minutes left. Wow, I talked for so long, for so short of a time. Sorry. Our ZK EVMs endgame. So this is probably the spiciest thing, right? Because I think you've probably been hearing a lot of rhetoric about like ZK EVMs, fast finality, like we want to be, I guess, on par with the latest developments in Ethereum. But there's something that's really interesting in terms of the ZK VM space. So ZK VM, you can kind of think of, it's relatively straightforward. You just take the Ethereum out of it. It basically enables, like I said before, computation that is provable, but this time it's more general computation, right? So you're not limited to whatever the EVM does. It's designed to support a broad range of applications. The cool thing about ZK VMs that has allowed developers to do is actually build circuits in languages that are more mature. Right, so if you're building circuits right now, you might build in something called Circum, right? When we talk about ZK EVMs that are being built right now, we're writing custom circuits, which requires custom security auditing, which requires, like, I guess, a very specific skill set. But with ZK VMs, what it allows you to do is actually do that same thing, but do it in Rust, right? You have a bigger pool of developers. Rust has its own like really cool like speedy things that it does. And I guess projects to look out for that are doing ZK VMs is Risk0 and Succinct. And this is really cool, actually. Like I mentioned before, of what this allows us to do is actually Succinct built something that allows optimistic rollups to start implementing validity proofs. Right? It's very, very new, but this is kind of the new space that ZK VMs introduce, right? The other thing, and like what that allows us to do, right, is accelerate ZK development in general. So when we think about blockers to privacy use cases, identity, et cetera, it's all like, you need a lot of, I guess, background information. But now you can do it stuff like Rust. And like I said before, the auditing surface is easier. And so I guess new things to look up, research, Zeth and SP1. ZK VMs are an interesting design space to follow. Okay, so these are my sources that I kind of was like looking through. If you want all of this information or want to read more, I had a pretty wordy slide because I feel like this is more useful as a reference. But this is a QR code to my beacons page, which has a link to the slides themselves. So feel free to save it. If you want to follow me on Twitter, feel free. I mostly post about frogs. So I guess follow at your own peril. Yeah, I think I have 47 minutes left. So I kind of screwed myself over with 47 minutes of Q&A. But that's everything. I think that QR code is supposed to allow you to ask questions over chat, but I'm also happy to just, no questions. Yes! Oh. No! Do I write about real frogs? No, I only post frog memes, but I'll tell you about my favorite real frog, because I have 47 minutes to talk about my favorite real frog. And my favorite real frog is the desert rain frog, which I have in a slide. Yeah. Cool. This is my favorite frog. And the cool thing about this is it never becomes a tadpole because it lives in the desert. It just immediately becomes a little frog. The end. Okay, cool. Have I seen The Good Place? I've seen parts of season 1, and then I fell asleep. If you can make it to season 3, there's a guy who really likes frogs. Okay, cool. Thank you. If we're all good, you can also find me, I guess, at the scroll booth where we'll have more swag for everybody who enthusiastically answered the questions. So, okay, cool. Oh, you have more questions? Well, I guess actually about SNARKs. Because they have larger proof sizes, and if I understand correctly,
right. Hello, everyone. Welcome to this next workshop. Hopefully you can hear me well. I'm wondering how to share my slides. Maybe I'll just wait for a moment for that. All right, here we go. Okay, how is everyone doing? I hope all of you had a chance to get lunch. You will need some brain cells to follow along. Although overall it's going to be kind of a beginner-friendly workshop. We're gonna do kind of a presentation first and then some Solidity coding. If you have some basic experience with Solidity, with smart contracts, or if you're just comfortable just reading code, then you should be able to follow along. So yeah, my name is Peter. I'm a protocol engineer at Scroll. And today I won't talk about Scroll per se, but I will talk about a new proposal that we proposed called RRP 7728 L1 S-load. So this is a new proposal that Scroll kind of implemented in a DevNet, but we hope that this will be adopted by multiple L2s in the future. So the hope is that after this initial 20-minute presentation, you kind of get the idea, like what is L1 S-load, what can you do with it, why should you care about it? And then for the remainder, myself and my friend RH will do like a Solidity kind of workshop. So we have 2 hands-on examples and exercises for you. Okay, so now you can hear me. I haven't said anything important yet, so yeah, let's kick off. Oh, by the way, before we kick off, if you have any questions, feel free to interrupt me, but also there is this Q&A function here in the app, so you can just click here. I think most people probably don't know about it. I don't think it's widely used. Feel free to submit any questions here as well. I will keep an eye on this. All right, so L1 S-load is a new proposal for rollups for L2s. It's a precompile that allows developers to build applications that read L1 state from their L2 contracts. We hope that this is a new functionality. It's not groundbreaking. This is something, if you're very technical or if you take on the cost, you can already do in your dApp. But this proposal makes it much, much easier. And we hope that this will unlock a lot of new applications. So I want to talk about what is L1 S-load, kind of show you the interface, how to use it, what are some of the use cases that we found so far. Then I want to get a bit more philosophical, like why do we want to offer this service on the protocol level? And finally, just some insights into kind of the protocol engineering part and the challenges of designing such a proposal. There's going to be another talk on Thursday where I will jump into much more details about these protocol level considerations. All right, so what is L1 S-load? So L1 S-load, as I mentioned, is a precompile. If you're familiar with the EVM, you know that there's the EVM bytecode that you execute. But there's also special contracts called precompiles that implement certain functionality. On Ethereum, on layer 1, this is usually like heavy, expensive cryptographic operations that will be very expensive to implement in Solidity. But we can also use the same mechanism to expose other functionalities to L2 smart contracts. So L1 S-load is a precompile, and you can call it from your contract, just normal Solidity code. And you can read state directly from layer 1, which is Ethereum. This is how it looks. How many of you are familiar with Solidity or has written Solidity? Okay, so I think you should be able to follow along. Basically, this is just a very intro example. The way you would interact with any precompile, including L1 S-load, is basically you can just issue a call to it, like a smart contract call. Here we use a lower level call called static call, and you just encode the payload. And with this proposal, the payload is simply a contract address, an L1 contract address, and 1, 2, or more storage keys. You can call it from your contract, and then you can decode the result. So this is actually fetching data not from the local blockchain that you're running on, which might be Scroll, it might be Optimism, it might be Arbitrum, any L2 that implements this proposal. Instead of that, it's fetching data from Ethereum L1 under the hood. So this is defined in an RIP. I'm not sure if any of you are familiar with this. So EIP, Ethereum Improvement Proposals, are used to propose new features for the base layer for Ethereum. And there's kind of a new initiative this year called RIP, which is a similar process for rollups. So Rollup Improvement Proposal. It's optional, so we can create these proposals. If you guys find it useful, then hopefully more and more rollups will adopt this. So just more details here. Why do we care about this? Why is it useful? This is kind of, as you say, it's kind of low level. Just looking at the previous slide code example, it's kind of hard to see what it's used for. Luckily, we've already run a couple of hackathons, and hackers came up with some great use case ideas in the past few months. And I think we have a similar hackathon just after Devcon. One of my favorite use case examples was a cross-layer tornado cache breach. So many of you might be familiar with tornado cache. It's a shielded pool. Basically, you can deposit your assets and then withdraw to another address, and you cannot correlate the depositor and withdraw address. So it's a privacy-preserving mixing pool. But you could only use it on L1, but you could use the same technology to kind of deposit on L1 and withdraw on L2, and this could be built using L1S load. Another use case is ENS. So ENS is still primarily used on layer 1, although they are exploring, supporting more and more L2s or deploying on L2s. But if you're on a chain that doesn't have ENS, then through L1S load, you can still resolve these domains just by reading the register contents from L1. There's also cross-layer reputation system incorporating data both from L1 and L2 chains. There's a bunch of DeFi application use cases. So for instance, you could borrow on L2 without bridging the collateral to L2, just using your collateral on L1. That's an idea that they explored. You could also implement these hooks for Uniswap to make sure that the L2 pool has enough liquidity and not too high slippage compared to the L1 pool. So kind of give more assurances to you when you swap. And you can also use other, multi-sig, A-wallet, key store use cases with this. So these are just some highlights, and I linked all of them here. You can check the slides if you're interested. These are very interesting projects that we've seen at hackathons. All right, so now you kind of have a general idea of what is L1S load. So let me jump into kind of why we want to provide this functionality on the protocol level. I wanted to give a quick walkthrough of rollups, but I think many of you were here for the previous session by Emily, and I prepared 2 slides, and Emily did like 50 slides, and she did a great job kind of telling all of you what rollups are, so I'm just going to keep it very short. So a rollup is an Ethereum that's inheriting a lot of security guarantees from L1, which is Ethereum in the case of rollups. So rollup create an L2 chain, and then package these L2 blocks into blobs, post it on Ethereum, and also post the execution results, which is the L2 state root. And then there's different mechanisms how you can verify the L2 state root towards a canonical bridge. So you can use fraud proofs, you can use ZK proofs. There's different pros and cons. So if you think about information relay between L1 and L2, when you relay information from L1, you need to usually use a deposit message or some kind of other message in a canonical bridge. And this message will be relayed by the sequencer in a verifiable way. So usually the sequencer would include these deposit messages where you can encode additional information, but the sequencer could also implement other functionality, for instance, relaying the L1 block hashes. The other way around, you usually need to first submit a withdraw message on the rollup, and then once this is finalized, you need to claim it on the L1 side. So slightly different ways depending on which direction you want to go. All right, so if you're a dApp developer and you want to read some data from L2 on L1, how do you do that? Well, you're lucky because you already have the L2 state root on L1. That's kind of an inherent property of all rollups that the L2 state root is posted to L1. So your contract can just read the state root and provide a Merkle proof, and then you can verifiably read any state from L2. The other way is basically the same thing, but it's a bit trickier because L2s usually don't have this notion of the L1 state root. So we would have to implement that first, but there's ways around this to implement it. And then it's the same thing. You provide a Merkle proof to read from L1. So it is already, without this proposal, it's possible to do it, but it's not very convenient. Like, how do you relay the L1 state root? How do you verify it? How do you provide this Merkle proof? It's a lot of extra complexity and overhead for the developer, as well as cost. So the idea here is all of this process, the second part, how to read L1 state from L2, is something that the sequencer could provide you as a service. So hide all the complexity from the developers, and you just focus on your application logic and just interact with this contract. So I would say it's Merkle proofs as a sequencer service. That's one way to think about it. If you think about this, how it's implemented by the sequencer, basically any call to this precompile is translated to an RPC call to an L1 node. So if you're familiar with the JSON RPC of Ethereum, there's one called ETH get storage at. That's basically what this precompile corresponds to. And then the tricky part is how do you verify it? So we also need to make sure either in the fraud proof or in the ZK verification proof that you also verify this, that the sequencer didn't cheat you. The sequencer actually relayed the correct message. As an aside, many of you might not know, like, why do we use a precompile? Why don't we use an opcode, for instance? It's mainly because of compatibility. So we want to maintain compatibility with existing tooling, with the EVM, Solidity compiler. If you add the new opcode, then none of the tooling knows about it. But if you add the new precompile, then most of the tooling can interact with it as if it were, a normal Solidity contract. So it's a much less invasive way to add functionalities that Ethereum might not have. All right, just a little bit more details about kind of the implementation. Because as myself, protocol developers for rollups and other rollup teams, you need to think very hard about how do you implement it, what are the possible attack vectors that this could open up, how do you verify the inclusion, etc. So the interface of the contract that you will also see in more detail in the Solidity example is we try to keep it as simple as possible. So basically, you just need to pass an address and then 1 to up to 5 in the current spec storage keys. So you can read up to 5 storage values from L1 in a single call to this precompile. And then the result is also just standard storage slots. If you're familiar with storage layout, then you know what this means. If you're not, then RH will tell you all about it in a couple of minutes. It's just returned to you, and then you can decode it. Implementation-wise, there's 2 main prerequisites that might be a bit controversial. So first, I briefly mentioned that you need to have this notion of what is the latest L1 block hash. Your L2 needs to have this notion. So either the sequencer needs to relay this with a special system transaction, or you need to have some other mechanism. But all the L2 nodes must agree on this, otherwise your execution would diverge. So I would call this feature trustless L1 block hash relay. Some rollups already have this. Others have designs for this, but not launched yet. In Scroll, the way it would work, and this might be different or similar to other rollups, is the sequencer optimistically relays this information, but any other node can verify it at this point. So if the sequencer cheats, then it's easy to detect. And when we finalize the batch with the ZK proof, that's when we verify that the sequencer actually relayed the correct block hash, because on L1, during finalization, we have access to this information. And the second prerequisite is that for reading L1 state, you need to have access to an L1 node, right? Which is already true for sequencer. So sequencer has to process these bridge messages. So they already connect to an L1 node. But currently, for some L2s, if you run a follower node, you don't need to connect to an L1 node. Now, if you adopt L1 S-load proposal, then you must always connect to an L1 node. So that might be an additional overhead for some node operators, but I would argue that this is kind of acceptable. Yeah, so all L2 nodes then must connect to an L1 node so that they can serve these requests about L1 state. And then just 2 more notes about implementation. So we have a reference implementation. I have a link to this in the slides if you're interested in our Go Ethereum fork. But basically, what you need to do is pretty simple. So you need to modify the EVM and add this precompile so that when there's a call to that address, which is specified in the RIP, then it triggers execution of this special contract. And when this contract is called, it simply starts executing an RPC request against the L1 node and waits for the result. So there's some complexity here that I probably won't go into too much, that like what happens if the request times out or the request fails. This can be an issue, and also this request might affect throughputs. But normally when you run your L2 node on the same machine, let's say, or in the same data center as the L1 node, this should be fairly fast and error-free. And once the RPC returns, you return these results to the EVM, and execution continues as before. So that's the execution part, and the second part is verification. As I mentioned, we need to keep relaying these L1 block hashes to L2. in a verifiable way. So in our case, at Scroll, for instance, we have a Solidity contract on L2. The only thing that the sequencer does is that it takes the L1 block headers and feeds them into this L2 contract. And the L2 contract actually does the verification that it's a correct chain of L1 blocks. And then once you submit this to L1 and verify it in a ZK proof, then we read the block hash, the correct block hash from the L1 EVM context and verify that this relay step was done correctly. And finally, so this first and second step is the trustless block hash relay component, but you also need to verify each and every call to this L1 load precompile. So for any precompile call, we need to, or the sequencer or the prover, depending on your architecture, it needs to fetch an MPT proof and it needs to verify that as part of the broader ZK proof. So this is something, all of these steps are steps that you would need to do as a developer. But now that this is part of the protocol and it's a sequencer service, you don't need to care about this anymore. You can know that it's working and verified. All right, a lot of details, just a few more notes about the next steps. So this RIP is fairly new. We just published it in June this year. There's a call for the RIP process called roll call. We presented it in July. And then, as I mentioned, since July until now, we had a bunch of hackathons where hackers and devs could explore this and play around with these proposals. And for now, we just want to continue this process, and we'd love to hear more feedback from developers, from protocol maintainers. Basically, once we can converge on a spec that everyone is happy with, and other L2 teams, at least 2 or 3 L2 teams, have some willingness to adopt it, then we can finalize the spec and start rolling this out in production. I think it would be awesome to get to that stage next year. All right, there's a few additional resources here for your reference. And I have, again, the slides here if you want to save them. But for the remainder of the talk or the workshop, we want to jump into more like hands-on coding. Before we do that, any questions? Yep. Yeah, so when you have a transaction that calls L1 load, then any node, be it sequencer or follower node, will execute an RPC call corresponding to this precompile call. For the validation. Yeah, so proving, it depends on your proving system, but I think we can say that, so the question was how long does it take to verify the whole thing? A couple of years ago, this would have been impractical because you couldn't have proven an L1 MPT proof in ZK. The technology was not there yet. But now proving speeds have been catching up and you have general purpose ZK VMs. So in our experience, this would add maybe a couple more minutes to the proving time. But it's not significant, and it will go down rapidly in the next few years. All right, there's a question here. Thanks for using the Q&A form. So what's the adoption look like from other L2s? How do we help? That's a great question. So we presented it at Roll Call. There's been some discussion on ETH Magicians, which is kind of the go-to place to discuss the proposal, but we haven't received too much feedback. The main feedback we've received so far is that devs love it. It kind of opens up the design space to devs that you would not think about normally. So that's very good feedback, but I'd love to hear feedback from other L2 teams, other rollups teams. If you can point out issues or anything that might break in the spec that we need to fix, the earlier the better, and then we can converge to a final spec. All right. So I'll just continue with the next section. So we have these code examples, basically 3 code examples of increasing complexity, although not too complex setup. If you want to either follow along, well, if you follow along, you can just follow the screen. If you want to reference this later, then you can take the code from GitHub. It has all the solutions. So if you don't want spoilers, then don't open it yet, or don't open the files yet. All All right, so you can see the editor. If the text is too small or anything, then let me know, and I can adjust. So I want to walk you through a very simple kind of toy example, just kind of to get a feel of how L1S load works from a developer perspective. Let me show you. So for this example, we will use Foundry. Many of you might have used Remix, Hardhat, Foundry. I think more and more people use Foundry. That's what we're going to use here, but you can use any of your developer tools that you're happy with. We're just going to do some fast development and testing on Foundry, and then RH will show you how you can also interact with a DevNet that we're running. So the simple toy example that I want to talk about is a counter. So let's say we have this simple counter contract on L1, and it maintains 2 entries in storage. So one is a simple unsigned int, and the other one is a mapping. So nothing fancy yet. And then there's only one function on it, which is to increment this number, and then to store something in the mapping. I guess counter is a bit of a misnomer because there's also this mapping, but you get the point. We just want to have kind of some state on L1 that we can interact with. So let's say you deploy this contract on L1, or someone has deployed it and you want to read from it. How do you read from it from L2? So for that, we will define another contract called counter reader. And the idea is that this is deployed on a different blockchain. This is deployed on L2. So let's say counter is deployed on Ethereum. Counter reader is deployed on Arbitrum or ZK Sync or any rollup that adopts this proposal. So when we instantiate this counter reader, we definitely need to have the address. So I have that pre-filled in here. So we're going to store the address of the L1 contract. And then the question is, how do you actually read from the L1 contract? So I'm going to show you first the low-level interface. And then we also have some helper kind of utilities that make it much, much easier to do this. So let's just go back to the slides for a moment. I had this slide previously. So this is a recipe of what you want to do. You need to ABI encode using encode packed the arguments to this call, static call, and then decode the result. So let's try to do this and see if it happens. So I'm just going to start by defining the payload. And the payload is, as I mentioned, it's an address. And we already have the address here stored. That will be counter. I could also call it L1 counter just to make it clear. And then it can be 1, 2, or up to 5 storage slots. So let's keep things simple and just focus on the first variable for now. Now, who knows what is the storage slot of this variable? Yeah, 0. This is quite easy here, but when the contract gets more complex, then it also gets more complex, like if you have inheritance, etc. So one thing you can do is, I usually use forge inspect. It's a kind of handy command. So you can use forge inspect, storage layout. I believe this basically just calls into the Solidity compiler, and this will show the storage layout of your contract. So we have number at slot 0, and the mapping is at slot 1, as expected. So I'm just going to go ahead and read slot 0. And that's going to be our payload. So we have the payload. Next step is to actually call the precompile. So to call the precompile, you need to have the address. Here in this helper, I already have this hard-coded. This is subject to change. So as I mentioned, the proposal is still not final. And also there's an interesting discussion going on, like what address should these L2 precompiles use? Should they continue at the same address range that L1 precompiles have? Or should they have like a dedicated precompile address range? I think everyone is leaning toward the second option. But for now, we're just going to use the same address that we have on our DevNet that we're maintaining. So we're just going to use this address and static call payload. And what this returns, if you're familiar with kind of lower level calls inside the EVM, is whether this call succeeded and the result of the call. All right, so we are halfway there. I'm going very slow because this is kind of an intro example. I think for advanced solidity developers, this might be a bit boring, but just hang on for a moment. So you got to make sure that this call succeeded. If it did not, then of course we cannot continue. Now it depends on the final spec. In the current implementation, there's no way that the L1S load fails. Once the transaction is included in a block, that means that the sequencer managed to fetch these storage entries. So it should always succeed. But unless, of course, you, for instance, encoded the inputs incorrectly. So you got to make sure that you do that right. So if it didn't succeed, we just revert. And if it did succeed, then we can decode the data. So the data, very developer friendly again, is just ABI encoded, so you can use all the solidity tooling or syntax to decode it. In our case, for now, this is going to be a single unsigned int. So this is the number, and I can get to the number by just ABI decoding this return value. All right, so we got to a point where we could read at least one of the storage slots. Now let's try to test it. And the test kind of also shows you, first of all, how you can develop with L1S load, and also how this toy example would work in practice. So I have a Foundry test prepared here. Kind of the very convenient thing about Foundry is that you can use Solidity for the whole development process. You don't need to switch to another language to write your tests. So in this case, we do run this test in Solidity, but the problem is that Anvil and Foundry, all this tooling is not aware of this L1S load precompile. So to make development painless, we created this class that you can use, or this contract test with L1S load. So this basically injects fake L1S load that behaves the same way as the real one into your test environment. So whatever you test with this should also work in the actual L2 context. And then the test itself is very simple. We just deploy the L1 contract. You can imagine that this happens on L1. For now, we're testing it in a single EVM environment. So deploy the L1 contract and deploy the L2 contract with the address. And then you try to read the contract. Originally, we didn't initialize the storage values, so all of them should be 0. Then we call increment. After this increment call, when we read from L2, you should see that the state has been updated. Let's see if that works. Oops. All right, so far so good. So we ran the test, it passed. And that means that actually when we called this read counter method, what it did is it called L1S load. L1S load fetched this storage from L1. And then it's returned to the L2 context. The only thing missing from this example is how do we read the mapping? Because if I uncomment this line, since we didn't implement this, the test will fail as expected. So how do we do that? Doesn't even know. So basically what we want to do is read the mapping value of this corresponding to this key of 1, 2, 3. How do I get the storage slot corresponding to this value? I wonder if anyone knows. Hash of the message sender? Hash is correct. Exactly. So some way you need to take the key, you need to take the slot, which is 1 in this case, hash them, ABI encode and hash them together, and that's how Solidity calculates these mapping keys. So it's a bit more complex, but if you know what you're doing, then not super complex. So let's try to add that. I just move this to another variable. Oops. It's actually quite hard to type standing here. Just hold on for a sec. So you need to ABI encode. I believe the first one is the key. It's something that you kind of got to remember, but RH will enlighten you in a couple of seconds about the details. So first is the storage key, second is the slot, and then you just take the hash. And let's see if that works. Maybe I remember it incorrectly, in which case I can just fix it. All right, so now instead of reading 1 slot, I read 2 slots. The call otherwise happens the same way. I just need to add this additional argument here. And also, when I decode the results, I need to decode it as 2 unsigned ints. So this will be, first one is going to be, let's say, value 0, and the second is value 1. And then just return this. So it's not fundamentally different from just reading 1 value or 2 values. Okay, let's see if that works. So now the test should pass. Yeah, question?
Yeah, but question or observation about the design of this. Like, for example, if you are understanding we want to read something on the same layer in a contract, one thing we can do is basically instantiating this contract at a certain address and read the data of the actual payment in this contract. So I was wondering that maybe this thing could be designed in the same way where you just specify, okay, I want this contract instantiated on layer 1 instead of layer 2.
Mm-hmm.
So basically, in this way, you don't have to specify the slot.
Oh, yeah, yeah. So that's a good point. I think the feedback is this is kind of low level. Like, who wants to deal with this? We could, if we could just call counter dot number to read it, this would be more convenient. And you can definitely do that. I think I1S load is just a building block, and it's very easy to build higher level abstractions on top of that. Actually, let me show you, and then we can get to the next question. So just wanted to show you this is how it works on a low level, but we do provide some libraries, a simple library in this repo if you open it. So instead of what you can do is I1S load read unsigned int and just provide the address and the slots. So I still need to define the slots, but the rest of the code is basically replaced by this single liner. So same thing, actually, just hidden in a library. So as a developer, it's probably much easier to interface with this. And also, we have utilities for unsigned int, for bytes, for address, etc. And also, this is still not as high level as you suggested, but using this, it's very easy to, I can create a contract or generate a contract that looks just like this, but is actually calling I1S load. Your question?
Is there any way to specify one or one just to make sure
Yeah. That's a really good question. The question was, can I specify which block I want to read from? Yeah. So that's a big challenge for sure. So in the first iteration of the RIP, we designed the interface in a way that you can also pass a block number, so you can read from arbitrary height. That's, for some applications, that's a must-have. For many applications, this is not needed. And it also requires you to run an archive node because you need to be able to always serve archive data. But basically, one of the open questions for the RIP, like, do we need this? Do developers need this? If yes, then we can add this. But in terms of reading stale data, that's still a challenge because there's a delay between when the data is updated on L1 and when this information is relayed to L2. So this delay can be reduced, but it's not instantaneous. Exactly, yeah. Someone commented on ETH Magician exactly about this. If you have any input for that discussion, we'd love to hear or see your comment. Any other questions? Actually, let me check the Q&A. We can get back to the more general questions a bit later. So that kind of wraps up the first example. Again, a very simple toy example, but kind of shows you the power of I1S load and also shows you how you can use this in your application without too much added complexity. Now for the next two sections, I want to hand it over to RH. Hopefully, I think many of you might be dozing off, my mellow voice and also digesting the lunch. So RH is full of energy and he'll kind of shake you up. Yeah.
So Peter's too tall. I have to just adjust this a little bit. So, hey everyone, my name is RH. I am so happy that Peter went first because mine is going to be dialing it down a lot level lower. To the extent that because it's a beginner workshop, we're going to be tailoring it for beginners who probably are not very familiar with Foundry as well, but they also just want to get rapid prototyping accessibility by using Remix. So we're going to be using Remix a lot. Shout out to the Remix team. And we're going to dive into the example first. Okay, while it's loading up here, I'm not too sure if I would be getting like bandwidth or if the demo gods are gonna be with me. So what I did over here was that I pre-recorded this and we could go through this. It's probably about 10 minutes, and then I'm going to be narrating over it as well. So 10 minutes, this is going to be like super beginner friendly. So for a lot of you, I'm seeing intermediate to advanced level devs, you're going to be bored out of your mind. And if you're bored out of your mind, hopefully I can sing you a lullaby and then put you to bed for a little while, take a little nap, and then be back up for a bit more of the complex types that we will be seeing. So in this section, in part 2, just a quick overview as well. We have done 3 hackathons so far, which uses L1 S-load. So through those hackathons, we have received like multiple feedback on implementation, understanding how to rapidly use it in different hackathon environments so that you can quickly tap into it and start building the application that you're looking for. So that is sort of where I will be leading this session, more so for like the implementation side of things. Alrighty. So let's jump right into the Remix demo first. This is going to be covering some setup in terms of like how do you want to set up your injector provider environment in MetaMask with the DevNet that Peter mentioned. We're going to be going through that. And you're all also in for some treat to watch me do a bit of debugging and watch my poor coding skills all on screen. And just before we dive into it, I want to give a quick shout out to Ahmed. I see Ahmed there in the crowd. He was the one who helped us to also put this together. So a lot of the credits go to him. Okay, so without further ado, we're going to first jump into Remix. So this is me writing the L1 sload demo.sol. Is this like, how fast is this? This seems like super fast. Let's do fast. Okay. All right, now I know that it's a little small because even I can't see it from here, so I've enlarged this. So in this L1 S-load demo, I'm going to do a quick demo on how you can rapidly create a layer 1 contract and a layer 2 contract. Just read L1 S-load with less than 25 lines of code just to see how simple it can get. So for this context over here, we are creating an L1 contract. So this would be on Ethereum mainnet. And in this case, since we're doing a prototyping version, it's going to be on Sepolia, we're going to be defining the first variable over here, which is number of type UN256. And we're going to be putting up a setter function. So this setter function over here is for us to override this number variable. And as we can see, number is equal to underscore value. And that's all that is required for the L1 contract. Again, this is a very, very simple example. We're probably going to be speed running through this because Peter did a way cooler job with Foundry. But this is also to cater to developers who are more accustomed to using Remix. So now moving on to the layer 2 contract. Yeah, fun fact about Remix, we can actually put layer 1 contract and layer 2 contract also in the same file. I found that like pretty cool. So the layer 2 contract itself, like what Peter mentioned, it could be an Arbitrum or whatever type of rollup in the future that decides to adopt this piece of technology. So very quickly, I am already defining the L1 S-load precompiled address over here. Again, I'll be sharing all of the resources on where we can find setting up for your DevNet. It's all here. So I'm just like typing it out, l1sload.scroll.systems. If any of you are bored right now, I'm just putting it up here also on the screen so you can also be very handy with checking out the resources that we have. There's a specific section here, DevNet, and it has a table outlining every type of information you need in order to get set up with interacting with the DevNet, and there you can see that is the L1 S-load precompiled address. And again, over here right now, we're going to be building the getter function for it. And this getter function will be the one where we call the number from the L1 contract. Again, this is me trying to be as verbose as I can, but at some part, not really. I think I do a pretty bad job. So you can come and provide me with constructive feedback later on. And we're going to be creating 2 arguments over here. We have the L1 contract address because we have to ultimately decide which is the contract address that we're reading into. And we also have to define the storage slot number. And over here, since it's a getter function, we're going to be returning a uint256. And oh yeah, this is just me showcasing some remix functionality. Again, we're diving into like what you can also do in remix here. So moving on, I've also written some comments on like what I'm about to do next. Probably should have done it in more like a to-do fashion. But anyways, we're writing a call function to L1 contract. We're not really defining the payload over here. I'm just trying to see what we can do with less than 25 lines of code here. So I try to be creative, not really. And over here, we are destructuring already this low-level call. And we are going to be packing the arguments, which in this case, it will be the L1 contract address together with the storage slot number. And then eventually, the destructuring of this process will return a Boolean of like the success and also like the payload. In this case, I'm defining it as uint data. And very similar to Peter's example over here, we will be defining like for success, if it's failing, and it's going to be reverting with an error message over here. Okay, I promise you, we've wrapped up really, really soon. Now we just have to convert the bytes. We have to typecast it from bytes to uint256 over here. So this would be the syntax in order for us to typecast it to uint256. So over here, very quickly, just now you saw my wallet address, and it's already set up to be with Sepolia network. So we're going to deploy this contract directly to Sepolia. And yeah, this is me being a lot more verbose. Now we're deploying L1 contract to Sepolia. So really, really beginner friendly here, like tapping onto like the entire spectrum of even aspiring developers here. Okay, so now we've deployed it. Oops. And after we've deployed it, it's probably a really good idea for us to also copy the contract address, which I did not do, but you can kind of see how the terminal from Remix would help us to gather that information later on. So I'm setting the number here to 7 just because we're at Devcon 7. Haha, found that was like pretty cool thought process, probably just myself. So right now, number is set to 7 on the layer 1 contract itself. So now we're going to set up our custom network for DevNet. We're going to go through this process of how it can get set up. Over here on the top left, you should be able to see like add a custom network. So over here, you just populate the information of network name, RPC URL, everything. You can just copy and paste it from DevNet. It's all set up for our convenience. There we go. So this here, I've already preloaded the address for Sepolia ETH. Now for developers who are interested in trying this out, the faucet is here. Definitely recommend you to check out the faucet. You get 0.1 Sepolia ETH for DevNet, and it allows you to like tinker with as much as you want. So over here, now that I've already added this custom network, we would then be able to directly deploy it onto DevNet. So that's us switching to L2 contract. And then we can directly deploy. Over here, I'm going to be showcasing as well what were some of those errors that I've encountered, so being very transparent as well. Notice that there is the transaction failure for not having enough gas. I'll also just be showcasing to some who are newer to Remix and also aspiring developers of like what you can do in order to get this to go through. So then we just have to bump up the gas. So what I just did was I just bump up to 1. Very, I would say, a simple way, a smooth brain way of treating this. By bumping it 1, then we are able to deploy the contract. So right now we already have this contract on L2. So over here, we're going to be passing on those to the argument, the input to the argument over here. We have the L1 contract address. So in retrospect, in hindsight, I should have like copied the moment that the contract was deployed on Sepolia. But even if it's not, you have a record of the past transactions in your terminal in Remix over here. Pretty handy. You can see that the contract address, if this would go away, is just directly tied to this contract address key here. So you can just copy that, and then you can just pass that over to your L1 contract address and storage slot number. Peter has done a great job already. Everyone here is like Giga Brain as well, so you already know that this is like storage slot 0. So I've also tried to be a bit more verbose so that people know that it's 0 index for how EVM treats storage slot. And you can see that we have successfully called 7 as the number, as a response. So we're able to get that information from the L2 contract. So there was also one thing that was lightly touched upon for the L1 S-load technology itself. So if let's say if it is in production, if I'm not wrong, it takes about 10 minutes in order for us to retrieve the information on L2. But if on DevNet, that's actually an artificial simulation, so it's actually relatively quicker in order for us to get the information. But over here, you can see that I'm trying to set a new number to showcase that it actually takes some time before we're able to read that data due to us simulating the L2, the delay of the time that we're getting the information from the L1 storage slot itself. So right now on L1, you can see that the number has been updated to 100. But when we're moving back to the L2 contract, it's going to take a little bit of time in order for us to get the latest information. So as a developer yourself, when you're building in Hackathon, if you come into this part where, hey, why am I not getting this information? It's like better documented inside the L1 sload.scroll.systems as to a bit of a delay for us when we're getting this information. But I can assure you that I would say it's almost about 20, 30 seconds ago, or around there for the time of my testing. This is me just like repeatedly pressing it in a way that I'm showing you that I'm actively interacting with the UI here. But eventually, sometime in about like 20 and 30 seconds, you'll see that the UE256, it will be updating itself to 100. So I think it should be now. This is also me going through the different types of transaction that we see. Yes, so it takes just a little while for it to update its information in order to get the information from the L1 contract address. So just like bear in mind when you're also building using like Remix, if let's say you encounter this issue, there's an L1 block import delay time. Yeah, it's better documented here. Feel free to also like check out the resource here. So this is actually me going through a very elementary way of what it's like interacting with the L1 S-load technology using Remix. So maybe I can pause here a little while to see if anyone has any questions. But I think like Peter done a greater job, and then he's covered like all the possible questions. So now what I think we can do is I want to touch on product refinement a little bit. And what I mean by product refinement is in the previous hackathons, we have different developers also trying to use different type of data types and different types of structures which are a lot more complex. We're going to dive into it and see how you can immediately implement it inside your code in the upcoming hackathon or whatever hackathon that you're looking at, or even if you're looking to just like build some cool shit, right? Am I allowed to say that? I hope so. But anyways, going into this, hopefully this is not too small. Let me enlarge this. Okay, so this is a pre-written contract. In order to like facilitate this discussion, what I've done over here is I also have a couple of contract addresses here, and I'm just going to be using them and load them in directly into our L1 contract. So over here, we have the first one, we have L1 contract. Okay, so for this demo over here, we will load this in directly into Remix. We're gonna pass that contract address, and this should be what you will see. Now again, all of this information, I want to highlight that it's already in the QR code that Peter shared. We have all the information over here, Devcon L1 S-load workshop. If you head over to source, and if you head into part 2 of the workshop, you'll be able to get all of the code here directly. So at the same time, in a way, you can actually be interacting with this as I am going through this demo with everyone over here. So very quickly, while we're just reading through this contract, we can see that we are defining UE256. There's a variable for it. And then there's also L1 text is what I've called it for string, and also bytes32, which is for L1 bytes. And some of them, I have left the comment, it's like storage slot at position 0, storage slot at location 1, storage slot at location 2. But the subsequent one, we're going to try to have a bit more of an interaction together with the crowd here. And you guys let me know what you think of the storage slot for the subsequent ones. We'll dive into them like later on. So we'll be also looking into fixed array and also array with smaller data types, for example, like a UN64, and then also with dynamic arrays. And then we're going to look at mapping, nested mapping, and also struct. So these are some of the data types and structures that we're using out there. Definitely there's a lot more complex ones as well, like what Pierre mentioned, there's also inheritance. But for the sake of time, with respect to the time that we have, now it's 2:50. Okay, we will be going through this example that I have. Again, it's a accumulation of the past hackathons that we try to refine the ideas upon. And for this constructor, very quickly running through with everyone, For L1 fixed array, we have already instantiated a contract with several input already. So you can see all of them inside here. L1 fixed array goes with like in the array of 3, 6, and 9, fixed array 2, 10, 20, 0, and 30, and so on and so forth. And the following ones, these are just setter functions and then also getter functions for us to kind of play around if you're interested. I know that in hackathons, it can get pretty, I would say, stressful. So you just want something quick and easy, copy and paste and start testing things out. So over here, we're just going to take a look at what it is like when we are interacting with the contract already. There are some parameters that I have already passed. So I think the state right now, it should be reflecting what it is. So for example, when we're getting retrieve number, you can see that, is it too small? I hope this is not too small. Okay, maybe this is better. So uint256 itself, for the variable of L1 number, it's already been instantiated with 100 over here. So there are a couple more. We're gonna go through my favorite, which is retrieve string. Retrieve string here, this is interesting. I love Devcon. I am super excited to be here with all of you. Devcon is gonna be the best time of our life. All right. But it's very interesting as well, because for string type, we're going to see how we can actually access the storage slot to concatenate all of the string, because as we know, it's only a uint256 for each of the storage slots. But for what I have passed over here, it's definitely like way more than that. It's not able to like store all of it. So how do we actually concatenate everything and then actually retrieve the string that you want? Because there are some hackathon use cases that I've heard of developers wanting to also add maybe like a URL to create like different types of profiles, and then like have it live on like L1. So this is why we have the example for retrieving string and how do we like concatenate all of it. And if we don't, what happens? We're gonna be going through some visual illustrations of that as well, because the best way to show is by, visual representation. And then for struct, what we have set in place is that we have, let me quickly go through the struct over here. We have the name and we have age, and then some of the information that we have already put in place is like Alice is 20 years old, Bob is 21, Charlie's 22, and these are the 3 pairs that we have. And then very quickly, a quick run through as well. If we retrieve bytes, you can see that this byte is not all zeros. You've got 1, 2, 3, and 4, 5, 6. For the sake of time, I've already run some of this information. I've already spit it into this like contract address over here. So, which is why you can see that this information, they are not just 0. If let's say it's just instantiated, you're gonna just be seeing zeros. And if let's say we retrieve like a dynamic array, again, we have instantiated it over here. You can see that it's 100, 200, 300, 400, fixed array, 369, and also fixed array 2, 10, 20, 0, and 30. So we can kind of see that, I'm not lying, this is my proof of work, that I've done my homework. Everything here, it is correlating to this address which has been instantiated. Okay, so that is a high level starting point to get everyone accustomed to what this contract look like when we're trying to call it like using Remix. So now, onwards to the fun part. The fun part would be to look at L2 contract. How do we actually interact with L1 contract? And for this example, I have also deployed the contract already because I feel like demo gods are never always with me. So I just try to prepare myself as best as possible so that everyone have a smooth brain experience, just like me. Okay, so for 2 of this contract here, we have the basic L2 contract.so, and this is going to be touching on more of, I would say, just 3 data types that we're looking at. We're going to have a retrieve for L1 number, which is the L1 number. And then we also have the L1 string. And then we also have the L1 bytes. These are just the 3 data types that we're looking at. So I would say this is probably the beginner version before we move into the more advanced type of manner of us calling the different, more complex data types and data structures. So for L2 contract, what we're first going to do is we will first change our network. And for network, I have this as scroll L1 S load. And we will also just copy the address which has been deployed over here. Again, we're just working with Remix over here. So everything is, already set up. Okay, so for retrieving L1 number. So what we're going to do right now, we are going to be reading through the contract together with everyone. Again, there's like multiple ways of us actually setting this up. We can even use the contract that we're planning to read and pass it on as an argument to the function itself. But for the purposes of this demo, in order to kind of like speed run this as well, what we have done is we're instantiating this contract directly with the L1 S-load contract address, in this case, which was the L1 contract previously that we've seen here. So in this case, when we call retrieve L1 number should return us 100 over here, yes. And so when we take a look at Peter's demo as representation, basically I didn't exactly define the payload as a line by itself, that's the only difference, but everything else remains the same, right? So a lot of the pattern, this is me going through the same patterns, running it through in a recursive fashion. So you can kind of see that actually utilizing this technology is not very difficult, even for aspiring developers. This is what I would like to try to instill to everyone here in the audience, I'll say. So we're retrieving L1 number, public view returns U256 over here. The slot number, over here, I have defined it already in the local variable as 0, because in the L1 contract, again, L1 number variable, global variable is at location 0. And in order for us to destructure this call here, it's a very standard syntax, I would say, for us to destructure the information. We get the payload, which is data, and then after that, we typecast it to U256 in order to get the result of 100 here, which has been set in L1 contract. Now, okay, L1 string, I'm going to touch on that a little later. I have bytes underneath here first. So we're going to touch on bytes first. Very similar also. Again, the only difference is that what we're returning right now is then bytes memory. And for the slot number, for the L1 slot number here, it's at location 2, I would say. So this would be what we would be officially passing through to it. And when we are calling, making this low-level call, we're essentially calling this address here, this L1 S-load address is reading from here that we've defined in the global variable. And we can create this low-level call, and then we pack all the information, the contract address and the slot number, we concatenate both of it in code pack, and then we make this call to effectively retrieve the data, which is in the form of bytes. And when we call it, we can see that it is exactly reading to what was the L1 contract result like. Now, for string type, I find that string is quite an interesting piece of information. I've heard some of the audiences are already very familiar with how to actually retrieving the information. So I feel like there are a lot of like intermediate and advanced level devs here already in the audience. So this is like fantastic also. And what we're going to do is just kind of like rehash some of these concepts that we have seen. And for string over here, I mentioned like test slots, for example, because there's a limit for us to store information in each of these storage slots. It goes up to like only U256, for example. And so because of that, there's like limitation for each of these storage slot. What then happens is that we actually have to add we have to create a while loop in order for us to concatenate all of the string information together and then return like what we have initially like passed at the start of it. So for example, right now, string storage slot is located at location number 1, but if we were to pass on maybe the test slot of 0, because it's always going to be indexed at 0, you can see that what it's returning is I love Devcon, I'm super, but then it stops over there. But if let's say we were to create a while loop for it, so as long as while it's true, we are able to concatenate all of the string data together, it should be able to help us concatenate the entire string result together and give us what we have passed. Like, I love Devcon, I'm super excited to be here with all of you. So that was me like speed running it. So let me dial it back and then we kind of see step by step of how we actually retrieve the L1 string. So over here, the L1 slot number is still at location number 1. The slot sequence here, I've noted it as 0 because it all starts at 0, but eventually we're going to add the sequencing to just keep adding it incrementally so that it can fully concatenate itself. We're going to be defining string memory string result as empty at the start of it, and while it's true, again, we're going to be making a low-level call over here, and this is where it gets a little bit more interesting. We have the L1 S-load contract address, but I've heard some from from the audience mentioning that we have to hash it. Exactly, that is correct. We're going to hash it, and then we're going to typecast it to uint256. And then we're going to add the slot sequence to it. So whenever that is true, we're going to incrementally increase the slot sequence because we know that there are still more information after that slot. And what it looks like is because if us hashing this data subsequently, if let's say it returns similar like 0x0000, it will then break. But before it breaks, as long as it stays true, it's just going to concatenate everything and return the string result. So this is like a high level of how we can actually concatenate everything and retrieve the L1 string result here. Okay, so again, all of this information, we have this code directly available inside the L2 contract here. So for devs out there who are excited to just get started with like tinkering with this, here's one for all of you. Okay, and then for the third piece, third and final one, I know, I'm putting everyone to sleep right now. We're gonna try to make it fun for the last one. Okay, so for the last one over here, we have the L2 contract advanced type here, and we're going to replace this with this contract. All right, so for this here, it will be a lot more interesting because we'll say that this is a bit more complex with different ways of actually querying the information. But very similarly as well, we're still defining the L1 sload precompiled address up front over here already. And the L1 sload contract address is because when we're instantiating this contract, it's directly using the L1 contract address, and so that it stays as a global variable here. We're also defining the L1 profile struct already, which means that we kind of need to create the data type for what is an L1 profile struct. Take it in a way that we are creating profiles for our people. This is a simulation and an example of this. So over here, if let's say we were to retrieve fixed L1 array, we're going to be walking through the first information, I would say, retrieve function step by step. We're passing the variable storage slot. In this case, this variable storage slot will be referencing L1 contract where this storage slot location is. And then afterwards, similarly, because it's an array, the way to access it is that there's going to be subsequent location that it is stored in. So what I've done is we just like add it in. Of course, there's like different ways of approaching it, but I felt like it was a fun way to also get the audiences like engaged to see where people think the storage slots are. But everyone's so smart, so I think they can get it. So very quickly, if I were to just kind of get the audience to think about where do we think is the L1 fixed rate storage slot at? This is storage slot 3. Dang, that's good. All right, 3. Okay, and maybe just a quick one. We're going to plug this information in if we are going for retrieve fixed array element here. And we say that the storage slot is storage slot number 3. And then array slot would be, we'll say 0 because it's all 0 index. And we call it, you're going to get 3 because 3 was already instantiated in the contract here as position 3 as well, storage slot 3. But what about for 6 and 9? Where is the storage slot for 6 and 9? 4 and 5. I hear 4 and 5. That's cool. So let's give this a try. We can go to the contract here. And because what I've done is, one way to think about it is it's just going to be added sequentially during the contract instantiation. So when we are creating the contract, already deploying it, there's like 3, 6, and 9. So 3 itself would be occupying one storage slot, 6 would be occupying another, and 9 would be occupying the subsequent one. So what I've done here is that when 3 plus 1 is essentially storage slot number 4, and you're going to be retrieving 6 as the return result over here. And the way to access this information, you're going to start seeing very repetitive type of syntax. It's also encode, it's using ABI encode pack, where we access the L1 contract address, which is from L1 contract. And then in this case, it's just a variable storage slot plus array slot. Again, we can always argue that we don't need array slot. The reason I've added that in here is just to show what we're really thinking about. We're just like adding the array slot based off of the length of the array. But in this case, actually, for variable storage slot, we could have just mentioned that this is variable storage slot of 4, but the array slot, let's just say if it's 0, we should still just be getting 6, because technically this is storage slot of 4. Yes, so we'll still be getting 6. Subsequently, if we look at dynamic array gets a little bit more interesting because during contract instantiation time, it's more of the length of the array that gets recorded into the storage slot itself, but the data itself is stored somewhere else, which we will need to access it differently. So if we look at this low-level call over here, there's actually ABI encode pack, and then we have the L1 S load contract address, and then we are hashing this variable storage slot, and then we are actually adding subsequent array index on top of it in order for us to get this, to retrieve the dynamic array number. So if we were to look at an example over here, if we look at L1 contract, so we jumped into like dynamic array over here. Yes, we jumped over to dynamic array. Very quickly, what do people think is the L1 fixed array to storage slot? 6. Is it 6, 7, 8, and 9 though? Why is it not 6, 7, 8, and 9? Sorry? It comes up to you in 256. Yes, that's correct. So actually, this occupies like one storage slot by itself. So just storage slot 6. Again, I feel like the reference from the visual representation, visual illustration from Peter using like Foundry to check out this storage slot, that is like really helpful to also look at it. But this is also us going through the example, through the lenses of like Remix and see what we can actually identify. So the storage slot here for L1 dynamic array, it is actually, yes, storage slot 7 then. So for us to access the storage slot 7 over here, we're gonna pass 7 as the input, and then for array index here, it's going to be 0, and then when we call it, we're going to be getting 100. And 100 matches with what we've instantiated also as 100 over here. But the way that it is, the way for us to actually sequentially call the variable, the information of, in this case, the uint256 information, we're going to be adding incrementally +1, because that's how the information is packed in the storage slot. So it gets hash, and then it gets typecasted uint256. Every subsequent number that gets pushed onto that array, it will be occupying that slot respectively for the value. So even though when we push new information on top of dynamic array, that is, we just have to add a subsequent new increment +1 to array index, and we're able to access that information and fetch it. When it comes to decoding this data, it's really, I would say, the same type of syntax that we see for retrieve L1 number. It's ABI decode, data, and uint256. Moving on to the next one. I think mapping is an interesting one, but because this example here, L1 address to mapping, this is fairly straightforward. We have the L1 address to number mapping, which maps this contract, which was instantiated already. The same address will then give you a value of 100. So with respect to time, I think I only have 20 minutes left. What I will do is everyone will be able to like reference this information over here. I will skip through retrieve L1 address to mapping, but instead we're gonna go through a cooler example, which I think has seen a lot of use case and a lot more interest, which is when we're trying to retrieve and resolve ENS handle. There was some feedback mentioning that there were a lot of nested mapping used inside of ENS contracts. Some of the feedback that we've also gotten was that it was relatively over-engineered. I'm not too sure, but to some extent, we would use L1 S-load, gives you the capability to access and resolve your ENS handle at L1, at layer 1 itself, right? So for this function, when we call the retrieve L1 nested mapping, this will be a bit more interesting in the sense that we have mapping address as a variable and also mapping string. And where do both of these arguments come from is that if we look at nested mapping here, where do we go? So for L1 nested mapping, it's essentially like an address that maps to another mapping of string to then finally resolve it to a uint256. So for us to resolve to the final uint256 result, there's like multiple ways that we have to first hash the slot in order for us to access that information. So because there is 2 levels of mapping over here, I would say, so we're gonna have to first hash the initial slot, and in this case would be like catch up to 256, and then similar syntax, ABI encode pack, We have our uint256 here with the mapping address. Mapping address, this will be the address that maps to this new mapping of string to uint256, and we're going to have to like pass on the variable storage slot. Now, do note that in this context over here, you will notice that this method of concatenation is that the variable storage slot comes later after the mapping address. So the way of hashing it, the way of accessing mapping is that we first structure the input, I would say to the left, and then the variable storage slot like to the right over here. And then as you have multiple levels of mapping, you would add on additional levels here. So for example, like bytes 32 initial slot, and then maybe bytes 32 like second initial slot, and so on and so forth. And then once we have the final slot over here, we're just passing the final slot information into our low-level call. And then since it's a uint256, we're then able to like decode this information directly. So let's give this a try. Over here, for L1 contract, we have initiated it with this address, ABC, and also 1000. And it should be returning a value of 1000. So this L1 contract, it is over here. And we have retrieve L1 nested mapping here. We will pass on the address here first. And again, for L1 contract, this is storage slot 7, so we'll pass on 7 here. And for string, what's for string? ABC. Let's do ABC. But when we call with ABC, we're getting a value of 0. Does anyone know why? Okay, I'm getting everyone to like doze off. So let me answer the question, because we're gonna have to follow exactly, more like a checksum thing, I would say, where we have to follow exactly what was being passed. In this case, it's supposed to be like an ABC. Let's see. And then we have this call. Then we should be able to retrieve this information. Let's see. Contract address. Oops, that is not storage slot of 7, because for nested mapping, it goes to 9. When we call it, there we go, the value comes up to 1000. So for those of you who are interested in understanding how to access nested mapping, this is a good example for you to start diving deep into. For the last example, I know I only have like 17 minutes left. I'm going to like speed run this. So for the final function here for retrieving struct, this is actually the same one. We have seen the same syntax like previously, and this actually goes back to mapping. So when we look at how the mapping for, there we go, gone through here. So for mapping, no, not mapping, my bad. This is with array index. It's very similar because the way that it is, yeah, so for like dynamic array number, the way that dynamic array stores its value, the way that it accesses the storage slots, dynamic array, they're very similar to struct. Actually, exactly the same. So for example, I'm going to showcase a quick example over here for retrieving struct. The variable storage slot, we're going to look into this again. We have 7 here, and then for address to number, we're going to say 8, and then here we're going to say 9. But for L1 profile struct, do we think that this also occupies a storage slot? No, the answer is no, so I'll say no. And then over here, it's actually storage slot of 10. And finally, over here, if we were to showcase the example of this, whoop, so for retrieving struct here, it's going to be variable storage slot of 10. And if we pass in 0 as the array index, we'll be able to get this value in bytes. But this is so interesting because the payload that we've defined, it comes out in bytes. So this could be like a homework for everyone to kind of like test it out, because this contract is already written. You can see that how you can access this information. But I've also created some utils over here for us to convert, for example, like bytes to string. So if I pass the bytes value that we've passed in, you can see that it returns like Alice in this case. So these are basically just like a set of contracts already written in Solidity for us to see what it is like implementing and trying to extract information from L1 using 2 different types of data types and 2 different types of data structure. So yeah, this is all I have. Does anyone have any questions? Or do we want to like go through everything first, then take questions like later? Yeah. Yes. Using the gas cost. I remember reading that there were some, but maybe I'm going to like get Peter to also like, but for like a general call, usually there's no gas cost. Yeah. But I do remember there was also a topic on this, but I will lean on to like Peter to also like talk a little bit about this. That's a good question. Thank you. Oh, yes, you have a question. Yes. Come again? You. Yes.
Under the first presentation, was mentioned proof of inclusion, and I was wondering why is it necessary if, like, through some machinery, I guess, you read something that you know that exists in the memory, or somehow, like, and also this proof of inclusion is something that is generated within this precompile.
Is it okay if I? Yes. Yeah, so we can probably spend the rest of the time on questions. There are some interesting questions in the form too. So I believe your question, maybe there were two questions, but the second one was, why do we need to have all this MPT verification?
Yeah, basically, if I read the memory of the storage, like some stuff that is written on chain, even if it's on a different level, like I know that it's there, why do I need a proof? And then if this proof is generated inside the compiler.
Yeah, so you as the L1, if you run an L1 validator, you know exactly the state, but you as the L2 node or you as the L2 contract, you don't. So what that means is the sequencer returns some value to you, to the contract caller, but the sequencer could just make up a value. We don't want to allow that. So that's why the sequencer, as part of the verification, could be fraud proof, could be ZK proof. It must provide a valid proof saying that, hey, I gave you this value and this is the actual value stored in L1. It's much stronger than an oracle. I guess, so I would say the sequencer optimistically relays this information. At this point, you can view this as an oracle, but you also verify it eventually. So there's like a period where you kind of trust the sequencer, and then eventually you verify it. So the sequencer long-term cannot cheat. So if you have two contracts, let's say on the same blockchain on L2, if one of the contracts exposes the storage, let's say a view method, then you can read it. If it doesn't, then you cannot. So usually you would need to call RPC. So that would be another interesting proposal, just letting you to read arbitrary slot from other contracts. Maybe that's a bit too invasive. It's useful for as a building block between L1 and L2, I believe. But for L2 to L2 applications or L1 to L1 applications, I'm not sure if this is super useful. Yeah, the proof of inclusion is just a verification. So that's kind of the second step. I think there's a related question before we go to other questions. Someone asked, can I utilize L1 load to call a view function on a contract? That's an excellent question because there was another proposal that's called L1 call, which is exactly about that. So you would call this also a precompile from your L2 contract, but instead of this very low level access to storage, you would trigger a view function, which is much more powerful and safe in a way. The problem with that is that it's much easier to verify it. So for instance, scroll, we have a type 2 ZK EVM currently. We have our own prover, and it works for scroll. But for L1 call, you would need to spin up like a whole different execution environment, a type 1 ZK EVM, and create a proof for that single call, and aggregate that proof together with your original proof. It's not impossible, but I don't think it's practical at this point. So L1 load kind of fills the gap of giving you something useful and practical, but it's not as convenient as a call. I think we had a question somewhere there. If not, yeah, go ahead.
So one from the top. So about security, how confident can we be in terms of L2
Yeah, so that's one of the prerequisites that I said is that the L2 should have a notion of the latest L1 block. And the way we would implement it is that the sequencer of scroll relays blocks from L1. Now, how recent these blocks are is kind of a security parameter of the system. If you wait for finalization, that's the safest, but then you have to wait. There's like a delay of relaying information of like 10 to 15 minutes. If the sequencer is waiting for a couple of confirmations, then there must be a mechanism in the rollup that reorgs if L1 reorgs. So
is L1 block hash part of L2 block, or how do you, because at the end you need to do the proving, right? Retrospectively, right? So how do you
right, so the sequencer relays the L1 block hashes to L2. So basically, you could also read directly the L2 state root or the L1 block hash, sorry, L1 state root and L1 block hash from L2 state. And that's what kind of L1 slot gets access to. But it's a very valid question. Actually, that's one of the open questions. Like the sequencer could just stop relaying this information. Currently, there's no mechanism to force the hands of the sequencer to keep relaying information. So it's possible that you read stale information. We need to do additional work to support applications where this could break them. But in most cases, you could assume that the data that you read is maybe 5, 10, 15 minutes ago from Ethereum. Another question? No worries. Just a few. I think we're about to wrap up. I don't want to take any time from the next section. Just. You mean the roadmap? Like moving on, or? Yeah, so we do have an implementation, and that's what I linked before. So we do have this DevNet, but it's not production ready yet. So that's why it's only a DevNet. It's not part of our testnet and mainnet. There's still a few rough edges that we need to figure out, and also we don't want to deploy it on mainnet until at least 2 rollups adopt it. Like this is only really useful if multiple tools support it. And to say why, I just want to mention that we have a third example that we didn't get to today. If you open the repo, then you can see it, and it's a key store. The idea of the key store is that you know we live in a multi-chain world. So you might have your wallet, your AA wallet, some whatever you prefer on multiple chains, and it's usually a multisig, so you can have multiple signers, multiple keys associated with it. Now in this multi-chain world, this becomes very inconvenient to maintain. If you want to add the key or remove a key, you need to do this again and again for all of the chains, and it can be 5, 10 different chains. So the idea of the key store is that, let's say you have a key store contract on L1, and the whole purpose is to manage keys. You can add and remove keys, and all your wallets that are deployed on, again, Optimism, Scroll, Arbitrum, they read which are the authorized key from L1, and they just use this. So you can update it in one place, and it automatically updates with some delay on all these other chains. So that's kind of to show an example why it's only useful if it's multiple rollups that's supporting it, because these use cases are really unlocked by this feature. Yes, so each of the rollups will need to implement it, and because rollups work differently, there might be, so the specification and the interface would be the same, but the details of how it works might be different from rollup to rollup. So that's kind of an implementation detail that's left to the rollup team. Apologies, there's a bunch of questions that we didn't have time to answer. If any of you are interested, either devs or protocol maintainers who are interested in adopting this, I'd love to chat with you. So find me anytime after this session or later. And we also have another session on Thursday, 5:50 p.m. about the same topic. That's all for today. Thank you.
So
Test, test, test. Let's do. Test, test, test. Test. Test, test, test. Test, 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 test. Okay. Is it working? Okay, so please now all the team members go to one pod, take one pod. Everyone, all the team members, take one pod for yourself. So please, everyone, if you are on a pod and you don't have, so if you are on a pod, please raise your hand if you are the one who is leading the pod. Raise your hand if you are leading the pod. You are leading the pod. Here, what's happening here? What? So you are leading the pod, right? So I think here there is a bunch of people here. They don't have coins, right? If you don't. Which way? Here you don't have coins there. Make pod. If you are seated far away from the token, please stand up and go sit where there are tokens. If you are not near tokens, you will not be able to participate. So all this side of the room over there is going to be closed. Like all of that is going to be empty. Please stand up and go near where there are tokens. And I need the Wi-Fi. Yeah, I can take. I need the Wi-Fi. I need the Wi-Fi. Can anyone know the Wi-Fi? Or can you give me a Wi-Fi? I don't know if mine. Or can you give me a Wi-Fi? I don't know if mine is gonna work. I can try, but. No. There has been some issue. Wait, can we share the Wi-Fi? I will get personal spot. Is that the Wi-Fi of the conference? Yes. But what is it? You have the Infinite Garden? Okay, and what is the... What is that? This is the Infinite Garden? It's not connecting. Oh. The Infinite Garden. Test. So everyone, so all the people who are there and near tokens. Oh, okay. So you have tokens here. You have tokens here. Do you have tokens there? Oh, you are way too many here. They don't have cards. So this is gonna close. This is closed. Please get out of this. Find some place where there are people. This is closed. This row is closed. Okay. And are you seated in a pod? What is your pod? There is someone here? Oh, you are taking this? Okay. Okay, so can you take this pod? Take this pod? No, you need to take a pod. Like, take your pod. Min, do you have your pod? Min, take the pod. Okay. So let's start. So hi everyone. So today we're gonna learn about prediction market, and you're gonna be able to try your prediction market live. So let's start. So the goal is to learn about prediction market and outcome tokens, and your goal that the other player have. You don't want to have more tokens than the other. You just want to get the highest amount of token for yourself. So prediction market basics. So what is a prediction market? A prediction market is a way to make prediction about the future using markets where people can place order on what will happen. So for example, who will win the US election? You can get tokens of Trump, you can get token of Harris, and if Trump wins, well, the Trump token will redeem for some money. If Harris wins, the Harris token will redeem for some money. And by looking at the price of the token, you can make prediction about the future. So this can also allow you to get more complex signal, such as, for example, what will be the price of Bitcoin if Harris wins versus what will be the price of Bitcoin if Trump wins. And what do we need to make a prediction market? So you need a question, you need a list of outcomes, like who will win the election, for example. You need an oracle, you need a way to report the outcome of this market. So for example, Reality and Kleros, and I see the Reality founder there, and a lot of Kleros teams there. You need a time where you can start to resolve the market. And obviously, you need to get an underlying token, what you will earn if your prediction is successful. So the basic of prediction market, you will have one token that we'll call the underlying token. So here in my slide, it's DAI. Where you are here is going to be the coin that you have. You put it into this market, and then you will get one token of each of the potential outcomes. So here you put some DAI, and then you get some token for the Democrats winning the election, the Republicans winning the election, or something else winning the election. And when you look at the price of this token, that gives you some probability of this particular event happening. So we're going to start our first game. So before that, everyone, take for 500 worth of coin. So pod leader, give 500 worth of coins to everyone in your pod. 500 worth of coins to everyone in your pod. Oh, we don't have any pod leader there. With the pod leader, there is no pod leader there. Wait, can you be pod leader there? Yeah, lead this pod. What's happening?
The people at the back are empty. They need someone there. Or I could ask everyone to get up and shift.
There is no pod leader over there? Yeah. They have the coin or not?
They have coins, yeah.
Maybe Mick, can you take this pod? Do they have cards? No, you don't have cards. There is nothing here. I don't know how you even got the coin. So if you want to play, you have to go in some other pod. This has to be empty. So now, pod leaders, take the first sheet of MM which is cat and dog, and put a token where it's in bold, italic and bold on both of the markets. Put a token where it's in bold. Yeah, you have to take the sheet here and the cat and dog. The cat and dog. Everyone take a cat and dog. Is there a pod leader here? There is no pod leader here. Wait. Yeah, you take it and you put a coin. I gave you a coin on the bold stuff. So put the coins. So put the coins. Put the coins there. You don't. Yeah, this the small coins. You put the small coin for the AMM. You have it. You have it. You have it. You have it. Okay, this is working there. You have it. You have everything. Okay. You have here. Okay. What?
Need to repeat the first basics of the AMM, like just the first movement, because some tables.
There should be pod leader everywhere, and
Sorry?
there should be pod leader everywhere, like pod leaders who should be able to execute the AMM. So if any pod has some issue and do not have the dog, the cat or dog paper, raise your hand. If any pod has an issue. Okay, so as the market maker sheet, okay. So now what you can do, you can buy cat tokens if you think that it's a cat, or you can buy dogs token if you think that it's a dog. And the price is given to you on the AMM sheet. And what you can also do if you wish, you can give 100 coins and get a complete set of both. So you have opened the box A, right? You have all the box A? Okay, so now you can start to trade with this AMM, buying or selling tokens of cat and dogs. And if you have any question at any point, don't hesitate to raise your hand. Yeah?
How does the MM work? Like,
So
how do we buy?
you have your coins? No, you don't have your coin. Wait. Let me. I will come back with you. One. Wait, that was here? Was it not have the coins? So you need to have the coin here on your cat and dog. So you have the coin here, okay? So this means that you can, from the bank, you can buy token of cat at 50 and then you move it up, or you can buy token of dog at 50 and then you move it up. And yes, and you have to open the box A. Has everyone opened the box A? Pod leaders, have you opened the box A? Yeah, open the box A and you will see the token. No, that's the box A. So here we need a pod leader. Plinio, can you be pod leader there? Just take a seat here and take a seat and lead this pod. So what is here? We don't have pod leader here. Where is the pod leader? Are you leading a pod? Are you leading a pod? So here.
So each chip
each
Yeah.
100, they
That's
get
the,
one.
That's the cat and dog ones. You have the cat and dog in box A. So here, you can buy at this price, and you can sell at the price just above.
Any amount?
One by one.
So the circle.
You can have like, if multiple people want to buy at the same time, yes.
Dog at 50.
Yeah.
So,
So you
can,
have
I,
the
can,
dog
I,
token?
can I shove on that? Or what size can I bet before it moves the order
You
book?
can do one by one. So you have here, you have dogs. So give.
How much size can I put in before it moves the
It
order
should be,
book?
no, it's already one by one. So you have to pay 50. You pay 50.
50, okay. That's my max size I can do at this price?
And now it's moving. Yeah.
Okay.
You put that back into the bank.
Okay. I'm with cat.
You're going to be bag holding.
Then you will get the cat.
A cat bag holder over
This
here.
is here, and this is gonna move the cat.
Thanks for the exit liquidity.
The dog price is too good now.
So do we?
Any way we can understand what is
Yeah, because there should be a pod leader here. Why don't we have a pod leader here? Oh, you are here, right? Okay. Can you lead this pod?
So it's 50-50. I was talking with Rodrigo. Okay. Yeah, it's okay.
Do you have a pod leader here? Oh yeah, you have a pod leader here. Okay. Yes. Yeah, you have the coin. Okay, put it and start to handle your pod. Okay, here, here there is no. You have the pod? So, you are starting here, and every time you move, you are gonna move the coin. And what you can also do is you can give 100 and get a complete set, so both a cat and a dog if you want to sell them after. What? Cat and dog are in the card set in the pack A. It's in the pack A. Yeah, open it, it's inside. So, Claire, can you take this pod? Take the share here and take this pod. So,
So how, if they give me 100, they should get one?
if they give you 100, they get that and then the cat also.
Okay. So for example, he's giving me 100.
Yeah?
So
So,
what do I do?
what do you want to do? You want to buy cat or you want to buy dog? So, you can only give 50. You give 50 and you will get one token of cat.
Okay.
So 50,
Okay.
you get the token of the small one. 100 one. And you just put it in the bank.
60 for cat now?
Now you have to pay 60 for cat, or what you can do if you want, you can pay 100 and you get a complete set, so you get both cat and dogs. You can use it to sell it. But to sell it, you sell to the price above. You buy to the current price and you sell to the price which is just above.
Do you always have to buy both the set, or can you buy
No, you can either buy to the AMM here.
one more time?
You either buy to the AMM,
Okay.
or you are minting a complete set, so you give 100 and you get both. Yes? If you put 200, you will get both of those, yeah. You will get both sets. You get both sets if you put 200. And then after you can sell it if you want to take a position. No, you can sell it here to the AMM. You can go and sell it there. Yeah. Wait, here. Please, you need to be in the middle of the pod. It's not going to work otherwise. Go to the middle of the pod. Yeah. Can you move one here? Can you both move one on the right and go here? So what's happening here? Are you okay? But it's still at 50. Yeah. So, are you in a pod where there is a pod leader? Do you have a pod leader here or not? No. If you don't have a pod leader, go to a pod where there is a pod leader. Oh, you're the pod leader. Okay, so yeah. Are you handling the pod?
Can you please explain this part?
So
we can pay 100 to the market maker to get one cat
and one dog. If you pay 100, you will get one cat and one dog, right? Or you can pay to the market maker the current price, but you will get only one side. And when you do that, you're gonna move the token.
Okay.
If you buy one cat, the next cat is gonna cost 60, right?
Yeah.
Do we have to buy sell?
You can also sell, but you sell to the price which is above. And you move the token. Yeah, like the bank is gonna give you back the money. The bank can do you are the bank?
Yes.
You're here, and you will give back the money. So what do you want to buy? You want to buy a cat or a dog?
Okay, let's start.
You want to buy a cat.
I have 5.
So you give 100 to the bank, okay? You will get 50 back, and you want it to get a cat. And now it's moved, and now the next cat is gonna cost 60. Yeah, that's not the right cat. That's the the 100 cat. Yeah.
And is this one moved?
This is the dog. Yeah, and you can buy it, and it's moved.
Oh, it's
What?
independent.
It's independent. Yeah. Okay. So what are you do? What are you here? Do you have a pod leader here? You don't have a pod leader here, right? Oh no, you are the pod leader, right? Are you the pod leader? So you have cat and dogs.
We don't have the car, we all give to them already in the
Okay. So you have opened the box A. You gave the box A there.
How many cup do we need?
No.
How many cup do we need?
No, so you have the cat and dogs over there. So what have you done? Like you split into how many pods here? Are you how many pods? Yeah, just do one pod. No, like we should do 2 pods.
We have to split into the 3 group or we should try to
They have no pod leader.
Okay, they don't have the cards of the cat leader, right? They have no pod leader, none of these 3.
So can you do a pod leader? Can you do pod leader there?
All 3, but
But-
it's different planes.
Why do we have 3 things here? What is that? Why is that? This first, this is not here.
We should go down by how much what you put in was effective.
Yeah.
Possible to buy or sell more than one? No.
One by one.
One by one.
Yeah.
Prediction market.
Yeah. But that's gonna be hard to get if you just arrive now. Like it's already way more people than expected, so I can't get anyone in. Sorry. Yeah.
Does the price of one token influence the other? No?
No. So what you can also do, you can give 100 and get a set of both tokens.
We can do it in the middle of the round as well?
Yeah. So if you want, you can give 100 to the bank and get both cat and dogs. That can be useful if you want to sell them. Because here the price of both are increasing, so you can get some profit by giving 100, getting both a cat and a dog, and selling both. Yeah. If they are correct, yeah. So here there is nothing, right? Yeah, you sell it to the price just up, yeah. And you're moving the price. You sell both, yeah, and so you pay 100 and you got one, so you got 40 of profit. So it's not buying, it's minting, so you are minting complete sets. Yeah. For 100, you get both. No matter what the price, yeah. So do you have the pod leader here? And that's the current, okay. And it's back to 50-50, right? It moved up and down, it's back to 50-50, okay. Okay, why is the price still 50? Did you do? Okay, okay. Okay, so what do you want to buy, cat or dogs? You want to buy dogs, right? So, where are your tokens?
The one is a token. So
Where are these? So, and where are the cats? Where are the cats?
over there.
Why are the cats over there? Like, are you? Okay, here.
Because no one teach. Oh, I got it. What I understand. So here is the cat. Is a cat and dog, right?
Yes.
Oh, okay. Because this card is both like there's two categories inside, cat and the dog. Yeah. So we didn't know this card have to become a token to bet. It's not by using this one. Yeah. So you're going to like.
Just merge the pod, like just go all around in the middle and merge your pod. Do only one pod. You only have the one set of cards. It's only one pod.
Yeah. Okay.
So everyone move toward the center to make your pod. Put this in the center.
So do we still need a chip?
Put this here, okay?
Do we still need this chip?
You have your ship, right?
Yeah, 500.
So now you can buy cats and you can buy dogs.
So have to separate out the card, is it?
So you are the bank, right? Do you think you can handle the pod?
Huh?
You can handle the pod?
And the what?
You can handle the pod.
Like how?
So you are playing the bank, right?
Okay.
So if you are there, please go closer. If you are there, please go closer. This pod does not exist. This is the pod.
So I become a bank.
So you want to buy?
Cat.
Okay, so if you want to buy cat, where are the cats?
Yeah.
So you give 50? Give 50?
100.
Pay 50, you pay 100, right? You get 50 back, and you get a cat. And then the price of the cat is increasing. Okay? Everybody can do the same thing and get tokens of cats or dogs. Okay?
Oh, so right now, if 60, if you want to buy
cat, I have to pay 60, right?
Now you have to pay 60 to buy a cat.
Then going to 70.
And it's gonna go to 70, yes.
This doesn't move?
This doesn't move, no. But what you can do at any time is you can pay 100 to get a set of both cats and dogs.
Okay. This is first round. This is
Yes.
the only thing.
Yeah, yeah.
It's only one card. No matter how much I buy, also one card.
How much what?
No matter how much I bought, also one card only.
You will get 100 if it's a cat.
No.
If it's a cat, you will get 100.
Oh, okay.
I can't understand right now.
So let's say he want to buy, he have to buy 60, and then he will get one card.
Yeah, now you pay 60,
Then I'll get
you get one cat,
and then it
okay,
goes up, right?
and this is going up.
Because I think these two people for this one.
Okay, here. A consensus, yeah, that's okay. That's good.
We have dogs.
Is this
Yeah.
does this have it or else you have?
So what you can do is you can pay 100 to get both cats and dogs. And in this case, you can make some profit, right? Oh, no, actually, it's okay. Yeah, no, actually. So if you pay 100, you will get both.
And you can sell it back to the market. Just
And you
to
can,
balance things
no,
out.
no, you can sell it only, you sell it to the up. So you will sell it only for 90. So it's not gonna work. You're right, it's gonna work, but you're gonna lose money. So for now, the prices are good. Yeah,
One question.
yeah,
Can you meet multiple times?
yes.
Or there is only-
You can meet how many times, as many times as
Okay,
you
so
want.
there is not one
Yeah.
other.
Because I cannot hear. People are
Yeah,
talking.
show me.
No, I mean, people are talking. I cannot hear you.
Yeah, they should talk. They should talk is normal. So, what's happening in this pod?
If we sell a dog,
Yeah.
we get 50,
No, you get the price up. So you will get 40 only.
40,
40, you will get 40 only. So sell one by one. So you sell one dog, right? So it's gonna go here and you get 40.
Ah, okay.
So you get 40.
Okay. Now it's your turn.
You can, like, as long as there is no multiple people wanting to play at the same time, you can play whenever you want. If you are multiple, make a queue, but
Do we need
Yeah.
that to sum up 100 always?
no.
No.
It doesn't need to sum to 100. But you can give 100 and get both. Okay, so this pod is working, and you stay at 50-50. Okay. Yeah. You can trade with other players if you wish. It's okay. Minting does not move the price. No. Yeah. It doesn't need to sum up now.
It's a price. It's not a probability.
Yeah. It's a price. Yeah.
I think everyone has done purchasing and selling.
Okay, so everyone finish? So, please, if you have any last question, tell me before we finish the first round. What? Haha. What is it? Okay, any last question? Is there any last question? All the pods are working? Okay. So, everyone, we're gonna now stop the AMM. Oh, last order, we're gonna stop the AMM. Last order, last order. Do we have a last order? Okay, so everything is done. Perfect. So please, pod leader, close the AMM. And so now we're gonna first, if the price of the dog in your pod, the AMM are closed, it's not possible to trade anymore. If the price of the dog is higher in your pod, raise the hand. Of the dog is higher, raise your hand. Here the dogs are higher. The dogs are higher here, okay? The dogs are higher, okay? If the cats are higher, raise your hand. If your pod has cat price higher, raise your hand. Okay, cat price, cat price. So we see 4 pods with cats being higher and 3 with dogs being higher. And so now you will get the reveal. And that was the cat. So now, if you have dog tokens, they are worth nothing. And if you have cat tokens, you can redeem them for the amount of points written on them. Oh, okay, okay. Widely.
They are asking if they can keep the card as a souvenir or
Yeah, it's okay, they can keep the cards, it's okay. Okay, so did you all manage to redeem? If there is any question, raise your hand. So no question, let's go to the next element. So now we're going to open another market. So this is going to be a market about whether or not I'm going to say the word there in the mic. If I'm going to say the word there in the mic. So if within 10 slides I say this word, this specific token, the token on the left is going to redeem. Otherwise, that will be the other token which will redeem. So all the pod remove the cat and dog AMM. This AMM is over. And take the second AMM about this particular word that I can't say, or maybe I will say it. We will see that. Are you trying to trick me? So, if I say the word, you will get the token on the left, which will redeem. If I don't say it within 20 slides, you will get the token on the right, which will redeem. And Pan, where is the suitcase? I need the suitcase because there is your stuff inside. I need the suitcase. Where is the suitcase? You have to find out as soon as possible because if it disappeared, it's like endangering the workshop. Yeah? No, you can keep the card if you wish. Okay. Yeah? The question is whether or not I will say this word. Someone is trying to trick me. Where is Oh, here. What happened? Like, where is the content on my use case? Yeah, the content disappeared. Like, I have some content for the workshop which disappeared. That's probably number 4 or 5. It's okay. Yeah, it's okay. I have everything. So why interesting? So why interesting things? Because I see a bunch of people trying to make me say the word. So it's not necessarily the main goal of prediction market, but you could potentially use prediction market to incentivize some particular stakeholder to do a particular thing. You could see that. So here we have a participant who is saying that it's something similar to an assassination market. I don't think prediction markets are very suitable to make assassination market, but they could inadvertently become one. And that's why you have to make sure that your rule do not allow that. So for example, in Kleros, we have, as an arbitrator, we have a set of rules on what we can rule and what we cannot rule on. And markets which are unethical are going to be ruled as invalid. So they will not resolve normally. And this, for example, happened a couple of weeks ago, where you had a question about some Hamas leader being removed, like about some Hamas leader being in control of Hamas. And obviously, the most likely way that he will not be in control will be him being killed. So here the oracle returned that it was an invalid market. Yeah. 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 So for us, if the main source of uncertainty is something which is immoral, we will refuse to arbitrate. If there is other sources of uncertainty, like for example, if Trump was assassinated before the election, we'll probably arbitrate because the main uncertainty is not whether Trump will be killed, it's whether he will win the election or not. So the main source of uncertainty is the vote of the American people, not a potential assassination. So there, we will have ruled on this market. Well, at least that's for me, I would have ruled this market as valid. Yeah? You trade within your pod, only within your pod. Yeah. Yeah.
Sometimes they want to say in the exchange and the swing.
Yeah. If you sell, you sell to the price just above. So if you sell to the price above, and you move it. Yeah. It doesn't need to be balanced. The markets do not need to be balanced. If the markets are unbalanced, what you can do is give 100 coin and get a token of both, and you can make some profit. If you want, you can give 100 coin and get both tokens, and then you can sell them. You can always get both for 100. That's good.
If I have this,
Yeah. If you want, you can also give those back and get 100. No, you can. If you want to get 100, you have to give a complete set. You get the price just above.
okay, just above.
Yeah, just above. Yeah. Now? Okay, so sometimes markets do not resolve immediately. So this market is going to stay on because for now it's still undetermined. We still don't know if I'm going to say the word or not. And we're going to go to another market. So another type of market. Please, everyone, we're going to explain. Please, everyone, silence a bit. Thank you. Yeah. So another type of market is scalar market. So event, but we can also try to predict values. So for example, here, we will want to predict the inflation in 2015. And to do that, we set up a range. We can say from 0 to 10%. And now we will have some up token and down token. So if the inflation is higher than 10%, the up token are going to redeem. If the inflation is lower or 0%, the down token is going to redeem. But if the inflation is actually within the range, so between 0 and 10%, both tokens are going to redeem proportionally. So if it's 8%, the up token is going to redeem for 80 cents, and the down token is going to redeem for 20 cents. So this is interesting because that's how you can estimate value. And if you saw at the start of the workshop, I was showing you the Bitcoin price market. And this was a scalar market to estimate the value of the Bitcoin price. So now we're going to go to this market about my age. So you can go on the age market. And the goal is to find how old I am. So if I'm like 40, for example, the up token will redeem for 40, and the down token will redeem for 60. So everyone now, and keep the previous market. The previous market about the world, it's still open. You can still trade on it if you want at some point. So open the speaker age market. And in this market, You obviously know I'm not a negative age, and I'm not 100 years old. So the tokens are going to redeem not completely. Both tokens are going to redeem, but you don't know exactly for how much. So if I'm older, the up token is going to redeem more. If I'm younger, the down token is going to redeem more. Yeah? That's E. I know, but I'm not going to reveal it. At least not yet.
You always mean for 100. What?
You have B? You don't have B? I can give you a B.
They don't have speakers.
It was in the pack B. Yeah, it was in the pack B.
B or D?
B and C. There's
So if you are missing it, I have a pack B. I have pack
B
here.
is candle. B is candle.
no, there are
This is
multiple
weight.
things. There are multiple things. No, there are multiple things in each pack.
Okay.
It's not only one thing. So you have it. This is pack B. So you have it in the pack B also.
We don't have.
Yeah, sure.
Age down token. Is that for 70? Because the starting prices for these?
So starting there. Okay. So which token you want to buy?
By 30 up.
So you want to buy, so okay, so you pay 30. The price increases here, and you get the, no, that's the weight, that's not this.
This is the. That was an A.
So if you buy, so here you are not necessarily betting on something in the abstract. Exactly. So you should have your, like for yourself, you should have some estimate of what is my age. You look at the market. Is the market correct? Don't do anything. If the market you think is incorrect, you can either buy up or down, whether or not you think this market is too high or too low.
This market says like you are.
It says I'm 32 here. Here I say I'm 32 exactly.
What about the 700?
This is the price of the down token. The down token is going to redeem to 100 minus my age. So if you think that I am younger, than 30, you can buy the down token. Yeah?
Do you have 1 minute? I just wanted to.
Yeah?
I just came late, so I was going to attend this session. So what is this game all about?
Can you pick up a pod? pick up a pod and ask the pod leader.
Everyone verified the age at the end.
You need an oracle. And I'm working at Claros, which is an oracle.
Ah, nice to meet you. I'm from Reclaim Protocols.
Hi. Yeah.
You speak French?
Ouais.
Ok. Je pense que c'était pas sûr. La question c'est, en gros, si jamais je pense que ton âge il est moins que...
T'es où? T'es sur quel pod?
T'es sur ce pod-là, il a...
Let me see your face. For the guest, man. Okay.
I shaved 2 days ago.
It's gonna be a little bit younger, right?
What? The maximum is 100. So the age up token is redeeming for my age. The age down token is redeeming for 100 minus my age. Yeah. This is one is younger here. This is age up. Oh no, it's not age, sorry, age down. This one is age down. Age down. Yeah. So so here it's not about exactly just what you think. It's about whether you think the market is overvaluing or undervaluing. So here you have 68. So if you think that I am younger than 32, because you have to do 100 minus the price. If you think that I am younger than 32, you should buy. And if you think that I am older than 30, you should buy the up token.
Okay, I get it. Thank you.
I think I get it.
So how old do you think I am? 34 or 30? Yes? You need what?
What are we supposed to bet on?
So here, you are not making a bet in the abstract, but you are predicting whether my age is higher or lower than what this market is currently giving. Currently, the market is giving 30. So if you think that I am older than 30, you should buy the aged up token. If you think that I am younger than
How much you have to pay for that?
then how much do I have to pay?
What's the cost for that?
Well, it's here. You can see here. So if you want to buy the age up token, it's 30. And it's going to redeem for my age. So if you think that my age is above 30, you will make some profit. But if my age is under 30, you will lose some money. So you are not making a prediction in the abstract. You are predicting toward the value, not just an outcome, toward the value. And for that, you have to look at market prices. The age up is the one with an old guy, and the age down is the guy with the one with a young guy. So I'm 34 here, okay? I'm 36 here. Yeah. So if you think that I'm older than 30, you can buy age up because it's going to redeem for my age. If you think that I am younger, you can buy age down. Because because age down is going to redeem for 100 minus my age. No, you just put this one. This one is just like three. This one is just 3 of this. So don't bother with this one, just in case you had too many people. But
Okay.
This is the token you want to use, yeah. Yeah. So here you have to look at the market, and if you think the market is underestimating or overestimating my age. So here, if you think that I am older than 30, you should buy up. If you think that I am younger, you should buy down. Wait, you're done? So it's you for now you have to pay 70. And this token is gonna redeem for 100 minus my age. This one is 100 minus my age, this one is my age. Yeah? Yeah. It's 100. You can mint a complete set and sell the age down if you want to. So to mint a complete set, you give 100 and you get both.
Yeah, because if you give 100, you get both. So you can get that doesn't move the price, and then you can sell more.
Much diverging, that's a profitable strategy. To give 100 and get both. Sometimes you can make profit by doing that.
And this is the age up, like it's going to resolve to your actual age.
To my age, yeah.
It redeems as a function of his age.
Okay, if you have any last question before we close the market. Okay, so now we are closing the age market. The world market is still there, and I'm 32. So this means the up token are gonna redeem for 32 and the down for 68. I've looked at the 50 to 36, so maybe on average maybe 33. So we can see we had a pretty nice estimation of my age with this mechanism. So you can redeem your token. Yeah, if you have any question, don't hesitate to raise your hand and I will come help. Yeah? From Augur? Kleros is, let's say, a scalable version of Augur and also allows different sort of use cases because we have a tree of courts. We have a tree of courts. Yeah, so Augur is just doing prediction market. Well, right now it's not doing much because it's more or less dead. But for Kleros, you can have prediction markets, you can have anything, you can have curation, you can have some insurance, and as a juror, you're going to stake in a particular court, and you're going to be drawn in only in the court that you are specifically want to be participating in. And also, contrary to Augur, with Kleros, you will be randomly drawn. You don't allow everyone to stake on anything. It's only the jurors which are drawn. So most of the time, it takes only a small amount of work from jurors. And then Augur is a bit similar, but Augur also you choose your own dispute, while in Kleros you don't. In Kleros you choose your court, but not your own dispute. But both projects, at least like both mechanisms, are pretty similar because we are both taking this from Trustcoin. So Trustcoin was this chain coin mechanism made by Paul Stork, except the guy was a maxi, Bitcoin maxi, so he never managed to release the. It was Trustcoin. Trustcoin set up this mechanism initially, but they never released. Like the guy wanted to make it on Bitcoin, which was, I think, unfeasible. And UMA is looking a bit similar to Augur mechanism. Or Kleros. It's a mix of both, let's say, but it's everyone votes on everything. But also keep in mind, like Polymarket is using UMA, but in practice, like they have some admin key, so it's not like a real decentralized usage. Polymarket Oracle is working, so they're making a call to UMA, but also they have some admin, which can overrule UMA if they want to. And UMA is everyone votes on everything. Okay, so now we have another market, which is going to be a scalar market, the weight market. And here I have some item that we can light to make smell, made by Ponpon, by the way. And so what you're going to do is you're going to try to determine what is the weight in gram of this item. Someone's still trying. So you have this item. You have this item, and you have to try to determine the weight in gram of this item. So everyone takes the weight AMM, set up the weight AMM. You can still keep the word AMM. The word AMM is still there. And now you have the weight AMM, where you want to estimate the weight of this item. Well, if you are blind, you should probably not participate in the market. So if you want to see the item, I'm showing the item. No, you cannot feel it. You can just see it. Yeah. You can take a picture if you want to. No, you can touch, but you cannot weight it. Someone is trying to trick me again, you know? Yeah. That's the item. What is the weight in gram of this item? Yes, it is. Only look, only look. It's an item, it's smelling nice, you can smell it, you know. The item, it's to make some nice smell, you know, you can smell it. No, don't touch it because it will be unfair and I don't have time to. It's done by my girlfriend. So the item, so you try to estimate how many grams. Nah, there are too many people, so we will not have time to get everyone to. Hey, someone is cheating! Someone is cheating. But you can take a picture if you want to look at it a lot. It's just done by my girlfriend. It's not a brand, like it's made in my kitchen. This is the up token. The whole thing. It's the whole item, not just the wax, the whole item. So if the weight is above 40 grams, you can buy up. If you think the weight is below 50 grams, you can buy the down token. Only smell it, because it would be unfair. I don't have time to give it to everyone. So, did you all manage to determine the weight of this candle? Keep in mind, the markets are still open. The markets are still open. Yes? Yeah, the markets are still open. The markets are still open, keep in mind. I can print it. I'm the one who made it. What?
It's available.
I made it.
If they want
I
to,
can give you the file if you want
if
to.
they want to buy the candle more, they can stay back for the market.
Yes, you can still buy, yeah. So keep in mind, the market is still open. Yeah, it's still open. Oh, this market is still open. You can still trade. Yeah. This market is still open. You can still. Yeah. Yeah. Yeah.
That market was instantly closed? Or?
No, that's the point. That's the point I'm gonna make.
Ah, okay, nice. No.
Yeah. Yeah, it's still open. Yeah. Yeah. So keep in mind the markets. Both markets are still open. I can't unsay it. It's not possible to unsay it. Yeah, yeah, yeah. Oh, this one you can remove, it's finished.
I think that was something at the end.
Okay, so now we are closing the candle market. The market of the candle is closed. So everyone, silence please. Everyone, silence please. So here we had this market, and whether I will say the word candle. But the issue with this market is that we will not really know when we will know, because you will not know when I will say it, and you will not know when I will, or you will not know when I will go to slide 20. So for you, it's good. You are traders. You can make some money, like you have something which is known, and you can get basically free money by buying the token candle. But for the liquidity provider, it's very bad. And so for a lot of markets where we don't know when we know, it's extremely risky to put liquidity. Because as soon as the answer to the question is publicly known, people are going to jump on the AMM and take all the token of the right answer. So here, if you are here about the candle, immediately you're going to go to a price of 100, and the AMM is going to sell some token which at this point are publicly known to be worth 100 for way less than 100. So that's why you see most of the prediction market will be stuff like elections, because election you have a very cut-off date where you know when you know. But if you are making a market, for example, will the war in Ukraine stop? Well, you don't know when it stops or it doesn't stop. So for those markets, it tends to be extremely hard to get liquidity. So what you can do, you can subsidize the liquidity, knowing that the liquidity provider will lose money, but then they should get more in the liquidity subsidies. Or we will need to have other form of market makers which do not allow you to just buy and sell at any time. So we are working also with BCR on making some mix of AMM and auction, such that you have some 1 or 2 hour to overbid other people who are interacting with the market maker, specifically for market where we don't know when we know, to make it way less risky for liquidity providers. So this, for now, has not been implemented. That's just like a research direction, but it's a huge problem for prediction market to provide liquidity, the revelation loss. And so now, on the weight of the candle, the weight is 226 grams. You can that you can check here if you want to. If you don't trust the oracle, you can. It's on the balance there if you want to check. So this means that the up token are going to redeem for 100 and the down token redeem for 0. Oh, market is done. Oh, yeah, the market about the weight is closed. It's closed also, yeah. So now both markets are closed. There is no open market left. And you can redeem the up token on the price, on the weight, sorry. Okay, so what do we define here? We found a limitation of scalar markets. Please, everyone, silence, everyone, please. So we found a limitation of scalar markets in that you have to specify ranges. And if your outcome is outside of the range, just using the market price is not going to be very informative. We even saw that on most pods, the price of up was not even at 100. So we see like here we have a huge miss in the prediction potential. Like if the market was close to 100, you would have gotten the information that the weight is probably 100 or more. But here it was not even 100. So for scalar market to be good at giving you scalar outcomes, you need to have initial range which are good. And it's only an estimator of the value if this value falls within the range. You have to make the assumption that the value falls within the range. If there are some risk of the value falling outside of the range, you will end up with a bias estimate of this value. So another limitation of prediction markets. So now we're going to go to scalar market, multi-scalar market. So what can we do? We can estimate values, but we can also estimate proportions. So for example, we can make a multi-scalar market where we want to estimate how many seats in the European Parliament each party will get. So here, you don't take position on a particular value, you take a position on a particular share. So in the European Parliament, well, the amount of seats is fixed, but here we will see we will have a market where we don't even know the range, the potential range of the value. So let's go to this market. You can open the next two boxes. And here we're going to try to estimate how many participants do we have from each continent. So take the continent AMM in this room. Yeah. So you want to estimate the share of participants per continent in this room. In this room, yeah. Yeah, I know at the morning they gave you the global amount. So where you just were living before coming here? Oh, no, let's do where you're born. Like, where are you from? Like, answer the question. It's subjective. People may have different answers to that. The question is that I'm going to ask is where are you from? You have to put one here also? Oh, okay. Asia is... What? I can give you some. You can come pick up some here. Yeah. In this room, not the Devcon, in this room. That's the percentage, not the amount, that's a percentage. And you may not even know what is the total amount. So here you are estimating a percentage. Both? Yeah. So you're gonna need to. No, it's gonna depend what people answer. So if they consider themselves European or if they consider themselves Asian. Yeah. Okay, so the markets are closing. The markets are closing, and I'm going to ask you now. So please, everyone, the markets are closing. Do your last trade, and the markets are closing. Okay, can you close the market? Close the market. Markets are closed? Okay. Okay, so everyone, please, silence. Silence, everyone, please. So if you are from Europe, raise your hand. If you are from Europe. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 Europe, okay? If you are from Asia, raise your hand. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18, 19, 20. So 20 from Asia, okay? If you are from North America, raise your hand. 1, 2, 3, 4, 5. 5 from North America. If you are from South America, raise your hand. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. Oh, in Europe, I forgot to put myself, so that's 16. And if you are from Africa, raise your hand. 1, 2. 2 from Africa. And if you are from Oceania, raise your hand. 1. 1, 1, 1, 1. Okay, 1. So, let's do the total. That's 53. Okay, so now you have the value that the token will redeem. They redeem for the percentage, not the absolute value. They redeem for the percentage. And what's interesting is that we can show that you really were good at estimating that. Like I saw a bunch of pods where the price of Asia even went to the, maximum amount of value in the AMM. So you can see that it's a very good mechanism for doing estimation of the future. Well, here obviously I can't wait a week for a future event, so I'm showing you this event happening in a couple of minutes. But you can see that here on this particular room, the market were very efficient in estimating that. So everyone, you can redeem the tokens. You are redeeming? What? Okay. No, don't do the math. It's already written. So you don't need to do the math. I gave you the percentage in the slide. Yes? Yeah? I gave you the percentage. So they each redeem for the percentage. What? It's based on the percentage I gave you.
So this guy gets, how much money does he get?
38. Get 38 for the Asian token. For each of your token, you get 38 coins. We have one last round after that. No, we have a bit more because they were already late before. I have the prompter. Okay, everyone redeemed? Everyone redeemed? So if you haven't redeemed in your pod, raise your hand. If you haven't finished redeeming. Oh, okay. Wait, here. You redeem? Everything redeemed? Okay, so please everyone, silence, thank you. Please everyone, silence. So for now, we've been using markets to make prediction about the future, but the question is how can we use those predictions to make a better decision? So here in this example, you will have a market, who will be the candidate of the Democrat Party, and you will get a token of this market. But then you can put this token into another market, which will be which party will win the election. So here, you put some DAI, you get some Biden token, you put the Biden token into another market, and now you get a token which will redeem for DAI if Biden is a candidate and the Democratic Party wins the election. The other token, they don't trade for DAI. They trade for the underlying, so here Biden. So here you have a Biden Democrat token that you trade with Biden token. And if this token is worth 30 Biden token, you have a conditional probability that if Biden is a candidate, the Democratic Party will have 30% chance of winning the election. So you can change the market. And what can you do with that? Well, we're gonna start to show that. So I need a volunteer, someone who is not vegan. A non-vegan volunteer, please. Non-vegan volunteer? Okay, you can come. Okay. So the volunteer will have the choice of either trying a cricket snack or some fried fish skin. And here we have two markets. So one market on what will he choose, but after trying, he will give a rating out of 10, and you have market on this rating. So that's going to be conditional market. You will have a conditional market on what would be the rating given if he picks the cricket, or what would be the rating given if he picks the fish skin. So you can open the AMM with cricket or fish skin. And what is important is on the first two tokens, they are trading for coins. But then the other tokens, they don't trade for coins. They trade for the underlying token. So the first two tokens, they trade for coins. The four last tokens, they don't trade for coins. They trade for the underlying token, which is written on the sheet. And if you have any question, as usual, you can call me. You can participate in the market, yes, but please don't tell everyone. And so keep in mind, you can always mint complete set. If you want, you may not want to trade in the market of what will be the snack chosen, but you may just want to trade on the conditional market, on the rating conditional on a particular snack being chosen.
I will be back. I just have to go for a second, okay?
Oh.
I'll be back in a minute.
In a minute, okay, okay. If you have any question, raise your hand. Yeah? Alors, vous avez les... You have the token? Oh, they're there? Can you show the token? Yeah. Yeah, you have fish skin, but you have the smaller one. Yeah, put the smaller one, yeah.
The rating token for these, I find some for the plums and for the other things, but not the rating token.
You don't have them here? Can you check over there? I think over there. And so here you have tokens of like 10, 50, and 300. So if you are buying two tokens of 50, for example. For now, you don't need to use the 300. But so, for example, here, if you are paying, you can get two tokens of 50. But because this token, you can use it into those other markets. That's why we also give you token of 10s. And so here, first you can get cricket and fish skin, and you can open the last box. I think you will have in the last box. Yeah. Oh, because they gave us. I had the prompter with the timer here.
5:20. 5:20 was the time.
Because like I have here like it's giving like 17 minutes. Because the last teams they finish a bit later, so we don't have the 10 minutes to set up the space. But it's gonna be the last element. I do this one and after I finish it. Yeah.
I can bet on
Yeah. On what will be the rating if this is the particular SNARK which is chosen. Who was the guy who was chosen? No, he said he will come back? Yeah. Oh yeah, he's back, he's back.
If you think he's going to give it a good rating, you
Yeah.
say up. This is fish up or fish down? This is down.
That's up. What? Take what? No, but is there? Oh. Yeah. Yeah.
100 or?
No, 100.
I have to receive 4 of them.
Yeah. No, so you will get 100 of each. So that will be like 2 of 50 or 1 of 50 and 5 of 10.
Okay, so you have to do
Oh yeah, I saw. The guy is there. Okay. Yeah. Oh, no, the rating is out of 10. Rating is out of 10, yeah.
So, and also like when they mint, or then like no redeemable are for 100, so they can only mint for 300, right?
No, you put like 1 like that and 5 like that, for example. You need to do 100 total.
Yeah,
So if you mint a complete set, or if you buy here, you will buy well.
Could I mint this and this? For how much would
You can for 100. No, for 100 you will get that.
The 100 worth of these and 100 worth of pastry fish.
And if I would start,
And then if you want, you can actually take some position on those market while being neutral on those. You don't even need to make a bet on this. You can make the prediction only on the rating.
So we still quite confused after like.
Yeah. Oh no, so you get 100 total. You have the 10. Where are the 10? You have some token of 10s.
Token of this token or
No,
the
you
card?
have cards of 10 also.
I think there's somewhere in 10 for
fish,
10.
right?
No, here. I think there's something.
There should be some 10 somewhere.
10?
Well, fish, right?
Or fishkin, yeah.
I just gave you.
So here you have to buy with the underlying token. So here you have your fishkin. You can buy fishkin up or fishkin down.
Can we mint
You can mint a set by giving this, and you will get a set of fish up and down. Yeah. 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 And you can mint a set of fish up and down if you wish.
Okay, so in that case, I still have to give one more. And
What do you get for each of them? 100, 100?
100, yeah.
Exactly. It's one.
Okay, last trade. Last trade. Where is our volunteer? Okay, here. So, what we saw is that there are a lot of pods where both stay around 50, but you also have some pods where the cricket stays at 50, but the fish skin goes to 70. So you can actually use this as a tool to help your decision on what do you want to take, because you can see that because you can see the market believe you will get a higher rating to the fish skin than to the cricket. Okay. Because a lot of pods, they are 50-50, and you have some pods which are at 50-70. So here you can use the market as a tool to make a decision. So which snack are you going to choose?
I will choose the fish. And I do that from the beginning. So I took rights on fish.
Wow. The fish is chosen, and what is interesting here is because we had an actor which could influence the market, well, this actor took the token of what he was going to do. Okay? We'll let you finish it. So what is the rating out of 10?
7.
So the rating is 7. So you have the fish skin token which redeemed, and you also have the fish skin up redeeming for 7 and the fish skin down redeeming for 3. Oh no, all the markets are closed. All the markets are closed, and the workshop is also closed. That was the last. That was the last element. And so thanks everyone for coming to this workshop. I hope it allowed you to understand how prediction market works, how you can use those to predict the future, at least probabilistically, to evaluate potential future values, and also as a tool to help decision, as we saw with fish skin and cricket market. So thanks everyone for coming to the workshop. And if you could please help to put back the coin in the boxes, and the card, if you also put them in the boxes, that would be great also. So thanks everyone, and if you can help us for cleanup, that would be great in order not to delay anything. So thanks everyone for coming, and hope I got you interested in prediction markets.
Excuse me, sir.
Yeah?
Where can I get a set of these? Excuse me, sir.
Yeah?
Where can I get a set of these?
Otherwise, you can just take a set yourself here if you wish.
Otherwise,
you can just take a set by yourself here if you wish.
You have spare? You get it on
I
this
have a
again?
lot of them, so don't worry, you can take them. I don't spend noise. I think in my luggage. That's the my company, so it's okay.
All right, thank you.
you.